So, very good morning, one and all. So, it's my pleasure to welcome all of you to this event celebrating women in science and technology on the occasion of International Day of Women and Girls in Science 2021. It's an initiative taken by the Center for Nanotechnology Research, VIT, to celebrate the achievements of women researchers, thereby motivate young women scientists. The event CWST 2021 aims to celebrate the accomplishments of distinguished women scientists across the globe despite various socio-psychological challenges faced by women. Women constitute about 50% of the human resource, thus contributing a major strength in the socio-economic development of the country. They have contributed in almost every field: social, political, economic, and the scientific society. Science and society are closely linked, and hence there is an immediate need for a radical change within the social structure and scientific institutions. On an average, the proportion of women in science is less compared to the cumulative working women, and hence there's an urgent need to create awareness among the girls and women to take up science and technology as their career. We believe that this event would be a seed to create awareness and encourage women to be part of the growing science and technology. The event consists of 10 lectures by renowned scientists, 2 from abroad and 8 scientists from India. To further enrich the event, we have a fireside chat with Dr. Donna Strickland, Nobel Laureate in Physics 2018 from University of Waterloo, Canada. I once again welcome all of you to this event and wish you all to get benefited from the event. Thank you. So with this, we'll start the first session. So we have with us Dr. Shobhana Narasimhan. Thank you, ma'am, for accepting our invitation and honoring the event. It's a pleasure to have you here. And may I request Dr. Vimala to take over the session in introducing Dr. Shobhana. Thank you.
Thank you, ma'am. A very good morning to one and all. It's my pleasure to introduce Dr. Shobhana Narasimhan, Professor of Theoretical Sciences at the Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore. Dr. Shobhana completed her MSc at IIT Bombay in 1985 and later her MA and PhD from Harvard University, USA. She is also a visiting professor at Max Planck Institute for Metal Research, Department of Chemistry, University of Cambridge, UK, University of Paris, and the Abdus Salam International Center for Theoretical Physics. She has received several prestigious awards, namely Sri Shakti Samman Science Award 2010, Kalpana Chawla Women Scientist Award, the Government of Karnataka 2010, International Union of Materials Research Society's Young Research Award in 1998, Materials Research Society of India Medal in 2001, Institute Silver Medal IIT Bombay in 1985. Her main area of interest is computational nanoscience, and her research examines how the lowering of dimensionality and reduction of size affect material properties, the rational design of catalyst, gas storage, spintronics, nanomagnetism, mixing, and magnetism on surfaces. For these few words of introduction, now may I request Dr. Shobhana to deliver her lecture.
Thank you, Dr. Nirmala and Dr. Vimla, for the kind introduction. And it gives me great pleasure to give you this talk. So I will, 1 second. Okay, so I gave the title, My Journey Through Life and Science as a Material Girl. So I'll explain what I mean by that. 1 second, I'll just start my timer. Okay. So as I dare say, all of you are aware in your own lives, the world has changed a lot for women in India. So I thought I'd start a little bit with my personal story of my female ancestors. So I'll start with my great-grandmother, Lakshmi, She was born in 1902, and she got married when she was just 8 years old. She lived in Kanchipuram, so not so very far away from Vellore. And the story is that she was playing hopscotch with her friends when she was called and told, okay, now you have to get married. And she said, no, I want to play some more. And then her mother-in-law to be said, if you come now, I'll give you a mango. And so she would like mangoes very much. So she stopped playing and she went and she was married off. And as you probably know, in those days, usually if you got married at such a young age, you stayed with your maternal family until you were a bit older. But in her case, her mother-in-law didn't have any daughters, and she always wanted to be she always wanted daughters, so she kept Lakshmi with her already from the age of 8. And she also taught Lakshmi to read and write, and she taught her music. She was a very good singer. My grandmother, Sugandha, she studied school in Kanchipuram, and she got married at the age of 18, which was considered very late in those days. And she was also a very talented musician. And after she got married and had 4 children, she continued to study by correspondence, and she got a BA and an MA. My mother, Shakuntala, is also, again, a very talented musician and also a well-known journalist. She got married much later, in the sense she got married when she was 21, which again was considered late at that time. And she was doing her PhD when she got married. And within a year, I was born. And so she couldn't finish her PhD, which was something she always regretted. She was doing her PhD in economics. And then because she was at home with 2 children and couldn't work because of all the domestic responsibility, she started writing because that was something she could do from home. And she went on to become a very well-known journalist. And much later, after I got my PhD, I told her, Amma, now you have to go and get your PhD. I've done it. It's your turn now. And so much later in life, she went on to get not 1, but 2 PhDs. And this last picture is me. I look a little different in this picture, but it's actually quite a recent picture. And I have a PhD in physics from Harvard University. I also decided that I didn't want to get married. So as you can see, our lives have changed drastically over just 4 generations. So though I was born in Bangalore, I grew up in what was then called Bombay. And then I went to Harvard University for my PhD. And I did first postdoc at Brookhaven National Lab, which is in New York State. Then I went to Germany, to the Fritz Haber Institute in Berlin for a second postdoc. And after that, I returned to Bangalore and to the Jawaharlal Nehru Center for Advanced Scientific Research, where I have now been for 24 years. So this is my school picture. It was an all-girls school. It was a Catholic school. I will see if I can put on the pointer 1 second. Yes. So I think you will not be able to make out who is me. It's this girl here with 2 plaits. That is me. And it was an interesting school because though it was a girls' school, we were never told that you can't do this because you're a girl or you can't do that because you're a girl. And we really thought we could do anything we want. And I was not interested in physics in those days. In fact, I hated physics. My first physics teacher was extremely strict. She did not like me. And the way she taught us physics is that we had to memorize things. So I still remember the way we were taught Boyle's law in physics is we all had to chant it one by one. She would go through the class. So you have to chant the pressure of a given mass of an ideal gas is inversely proportional to its volume at a constant temperature. Then the next girl had to chant it. Then the next girl had to chant it. The next girl had to chant it. And of course, the end result was we had no appreciation, I think, for what physics was about. And most of us absolutely hated physics. And incidentally, if we got even one word wrong, we were kicked out of the class and we had to wait outside the classroom for the rest of the class. So after my ICSE, I went to junior college, which in Maharashtra state was not in school, but this was the what you call PUC or junior college. That's standard 11 and 12. And I went to St. Xavier's College in Bombay. And because of the funny combination of subjects I chose, I was in a class of about 75 students, of whom only 4 of us were girls. And after being in an all-girls class, this was a bit of a shock for me. And especially because after the first round of unit tests that we had, where I stood first in the class, the boys in the class all decided that they were going to stop talking to me. And so suddenly I was completely ostracized and I didn't understand what was happening. I didn't even know that the reason they had stopped talking to me was because I stood first. Only much later, many years later, some of these boys told me that, this is what we did and we're sorry for it. I never understood why nobody was talking to me. But these years, so though they were unhappy in some social sense, they were also happy because this is when I really discovered physics. I had some very good teachers of physics. And in 1979, there was the birth centenary of Albert Einstein. And I was asked to do a radio program for school students about Einstein. So to prepare for this radio program, I started reading up a lot of physics, and that was my first exposure to quantum mechanics and to special relativity. This picture is of the first day cover and stamp that were released in India to mark this birth centenary. And so I started getting really fascinated by physics, and I, in fact, became quite obsessed with physics. And I decided this is what I want to do with my life. I want to be a physicist. And I was lucky that I had very supportive parents who did not press me to do medicine, to do engineering. I think even if I had said I want to do arts or fine art or whatever, they would have supported me in this decision. So this is the picture of my parents, M.S. Narasimhan and Shakuntala Narasimhan, who are quite unusual in that they gave me total freedom to choose what I wanted to do. My father, M.S. Narasimhan, is a very famous mathematician. He's an internationally renowned mathematician. What I have put here is his collected papers and one of his more famous papers. There's something called the Narasimhan-Seshadri theorem, which is very famous in mathematics, which he discovered with another mathematician called C.S. Seshadri. My mother, as I told you, became a journalist, and she began to write a lot about women's issues. This is one of her books called Empowering Women. This is another book she wrote about sati. So she is a very strong feminist and believes in supporting women. So my father was, of course, very happy that I decided I wanted to do science. So I had a very unusual family background, perhaps. I also had a very unusual peer group in that I grew up in the campus of the Scientific Institute in Bombay. And my best friends there all were like me in that we all really liked reading books and we all really liked doing science. And so I've just mentioned some of my friends whom I grew up with. And most of us went on to do PhDs in the USA. So I've mentioned, for example, Ela did her PhD in biology at Yale. Sunita did her PhD in computer science at the University of Pennsylvania, etc., etc. There was only one close friend who did a PhD in English, but the rest of us all went on to do science. So I didn't feel that I'm doing something different by choosing to do a PhD in physics, because this is what my closest friends also all wanted to do. Then I decided to do my BSc in St. Xavier's in Bombay, even though I had the marks to go in for engineering or something. And the gender ratio was a little bit better there. We were about 1/3 girls in the class. And my master's, I went to IIT Bombay. We were a class of 12 only there. And of that, 4 of us were women. I then went to Harvard University as a PhD student in 1985. At that time, and even today, I think, Harvard was routinely rated as the best university in the world to do physics. And I was quite pleasantly surprised that I got admission there. Now, the gender ratio was again completely skewed there. So in my year, 1985, when I was admitted, so this is me when I was at Harvard, there were 2 girls out of a class of 30 students. And the next year, there were 3 girls out of a class of 30 students. This is 2 of those other girls who went on to become my good friends. And together we founded a group called Women in Mathematical and Physical Sciences at Harvard. Remember this woman, Elizabeth Simmons, because she will return in my story. I have to say that at IIT and at Harvard, I really became very conscious of how difficult it is to be a woman who's in a minority, a woman in science. For example, my first week in Xavier's in geology class, we were taught about cleavage of minerals. And the boy sitting next to me, who is now one of the most famous authors from India, he turned to me and gave me sort of a ha laugh and said, "Oh, cleavage, geology class is really becoming interesting now." When I was leaving Xavier's, several of the boys came and told me, "You know, you're the only girl I've ever met who was smarter than me." And I suppose that they thought it was a compliment, but I still found it a very strange thing to say, especially as these were not necessarily the guys who I thought were the smartest guys in the class. In IIT, I had things about me painted on the road. In IIT, there was some debate about, it was a debate competition about what should be the mascot of IIT. And one student said it should be sunglasses. To symbolize the blind eye they have to turn to the ugly IIT females. And nobody found this offensive. No one objected except me. When I was at Harvard, I shared my office with this big, tall French guy. And, when he was bored, he would just pick me up and hold me upside down. And he would call it inversion therapy. And many times when I was in Harvard, I would be mistaken for the group secretary. Since 1996, as I already told you, I've been a professor at the Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore. These are some pictures of our campus. This, as I don't know if you've heard of our institute, but it's one of the most well-known institutes in India. 2 years ago, Nature Index had a list of institutions in the world which were ranked, but they normalized it by the size. So we're a quite small institute. And when you normalize by size, we were pleasantly surprised to find that we were ranked 7th in the world. And if you see, we are 7th and Princeton University is only 10th and Stanford is only 11th, etc. So this is my group of students, and I am very close to many of my students. We've traveled together for conferences. I have gone through many looks over the years, as you can see. So this is me with some of my female students in Paris. In case you're wondering what we're doing here with our hands like this, I always joke that I am like the mother bird, sheltering and feeding my baby birds. So here we're acting that out, that I'm the mother bird and they are the baby birds. What do I work on? I told you I'm a material girl, so I work on designing new materials. So materials define human history and progress, so much so that the great prehistoric ages are named after the materials used in them. So you have the Stone Age, the Copper Age, the Bronze Age, the Iron Age, etc. And we design new materials. So this is sort of the periodic table made out of Lego, and the elements of the periodic table we use as our building blocks to design new materials. So I mentioned the Bronze Age. So bronze is an alloy of copper and tin, and it's harder than copper alone, and it does not rust, unlike iron. So what we do is what's called rational materials design. So we may study, say, 3 different materials. We do computation on them. We analyze our results. Then we get some insight into why these materials have the properties that they do. And that insight enables to design a new material with desired properties. So I'll just give you 2 or 3 examples. For example, iron and gold, though they're very common metals, it turns out you can't make an alloy out of them. They don't mix, they're immiscible. But we predicted from our calculations that if you take iron and gold and mix them on a ruthenium surface, it will form a stable alloy. And our collaborators in Paris did the experiment, and their experiments confirmed this. So this is a scanning tunneling micrograph of this. So these black circles here are a single iron atom, and they're surrounded, each black iron atom is surrounded by 6 gold atoms, which is the white circles here. So this is their experiment. This is our theoretical prediction. So this is a successful prediction. Another prediction we made, this is my student Nisha Maman. We predicted that if you have gold nanoparticles and you put them on a surface, they clump up into a 3-dimensional shape. But for various reasons, you would like it to make it a flat shape instead. And we predicted that if you dope the oxide with an electron donor, it will become flat. In fact, if you look carefully at Nisha's picture, you will see that her earrings, one is a 3-dimensional gold particle and the other is a flat gold particle. And again, the experiment was done this time by a group in Berlin. And if they put gold nanoparticles on a undoped oxide, they form these 3-dimensional shapes. But if they put them on a doped oxide, then they form these flat shapes. We are also more recently studied how nanoparticles move on surfaces, how they diffuse. So in this case, it is 3 platinum, a cluster formed of 3 platinum atoms, and it sort of walks in this fashion, as you can see in this movie. Whereas if you have 4 platinum atoms forming a cluster, then they don't walk along, but instead they roll around in this way, and we can calculate the diffusion barrier, etc. So that's all I'm going to say about my work. I can answer more questions later if you want. But so for my work, I typically travel a lot. So this was just something, you know, it was an automatic mail sent to me by Google Maps or whatever, which tracked, it's a bit scary to find it was tracking my visits in 2018. As you can see, I went all over India, I went to Africa, I went to many places in Europe. So I travel a lot for conferences, for conducting workshops, to teach, etc. Obviously, in 2020 and 2021, this travel has all ground to a halt because of the pandemic. So since we're celebrating women in science, let's turn to this topic. As you all know, historically, the percentage of women in science has been low. This is a very famous picture. It's a picture of the Solvay conference that was held in 1927. This is sometimes called the picture of the most brilliant minds ever, because nearly everyone in this picture went on to get a Nobel Prize. And you will notice, of course, that they are all men except for one person. This is Marie Curie over here. The other thing you will notice, of course, is that they are all white people. Okay, there are no people of color, there are no Indians, there are no Chinese, there are no Africans, etc. And how much have things changed? So this is a picture I just took from a conference that I attended in Shanghai in 2010. I could have put many other such conference pictures. Again, you will see it is almost all men. This time there are a lot of Chinese men because the conference was held in China. But if you look carefully, there are only two women in this whole picture. There's one woman here, and this is me over here. So, you know, a century later, things have really not changed much for women in science. So this is something I feel very strongly about. So there are two things that I do in addition to my science, my scientific research. One is I teach physics a lot in developing countries. So, for example, I'm involved with this initiative called ASESMA, which teaches physics in Africa. So this is me again in a new avatar. You see, I've gone through many looks over the years. This person in the red sweater is me at a workshop in South Africa. This is a picture of me with two of the women whom I have mentored, who are now faculty members after having been taught in part by me, one from Cameroon and one from Kenya. So let's talk about women in science. Now, I think many of you will be surprised to learn that in India, the percentage of women in science is particularly low, not at the student level, but if you look at people who are working as scientists, who have permanent jobs, etc. So this chart shows the percentage of scientists in a country who are women, and this is only data for Asia. Okay, and the highest percentage is in Myanmar and Burma, and India is second lowest in Asia. We have about 14% of our scientists are women. Only one country in Asia has a lower percentage than us, which is Nepal. So that means that Bangladesh, Pakistan, Sri Lanka, they all have a much, not necessarily much, but they have a higher percentage than we do. We have our absolute numbers of women in science are reasonably high because we have a large population of scientists, but the percentage is very low. And in fact, our percentage is sixth lowest in the whole world, which I think is a very shocking number. So if you look at physics professors, because I'm a physicist, I collected the statistics for physics. The blue bars here are men and the pink bars are women. You see that in all the sort of leading departments in the country, there are far more men faculty members than female faculty members. This is a picture from, I think, a couple of years ago. It shows the President of India, the Science Minister, the DST Secretary, the DBT Secretary, the directors of the IITs, the ICERs, etc. So these are some of the leading people in India in science administration. And the striking thing you notice is that there is not a single woman in this picture, which I think is a very, very shocking thing, that there isn't even one woman. Of course, we have had some very prominent women scientists, and I put one example of two women who have been very much in the news recently. This is Muttaya Vanita and Ritu Karidal. They were the project director and the mission director for the Chandrayaan-2 mission. And some of you may have seen this movie, Mission Mangal, which focused on the women scientists of ISRO. I didn't like some aspects of the movie, but I still think it's good that people are beginning to talk about women in science in India. These are again pictures that were sort of became viral about women in ISRO congratulating each other after the Mangalyaan Mars probe, etc. So now, if you remember, I had mentioned that I had a friend called Elizabeth Simmons at Harvard who was 1 year junior to me. So after we graduated from Harvard, we began to have parallel careers across the globe from each other. So I returned to India and I, rose up the academic ladder and finally became a dean, etc. And she stayed on in the US and she also became a professor. She became a dean. She's now the executive vice chancellor at the University of California at San Diego. But every 3 years, we would meet at what are called the International Conferences of Women in Physics, which are held around the world. So, for example, this is me and this is Elizabeth in Korea in 2008. And this is me and this is Elizabeth in South Africa in 2011. And we would talk, we would just chat as friends, but we would also talk about all the women who were our classmates, who were at Harvard at the same time as us, etc. And we got very disturbed by the fact that we found that most of these women were really struggling. They were having a really hard time with their colleagues. They were getting depressed. Some of them dropped out of physics. And we were disturbed by this. We thought, this is strange because these are the women you would think should be the most successful, if anything. And also in this conference in South Africa, there was a moment where a woman from Kenya talked about how when she became pregnant and she applied for maternity leave, which she was entitled to, instead of giving her the maternity leave, her department fired her from the job. And she said she was contemplating quitting. And then spontaneously, women in the audience stood up and said, "Sister, fight, don't give up. We will all support you." And I was very moved by this experience. And I thought, I want to do something for women in physics. And I also began to feel if women support each other, we can be a very strong force. So then I talked to Elizabeth, and together we decided we would organize career development workshops for women in physics. And we have been organizing these every 2 years at an institute called the International Center for Theoretical Physics, which is in Italy. And this is a very interesting institute because it exists, its mission is to promote physics in developing countries. So we've had women come from all over the world, developing countries all over the world, and we have these workshops to support women in physics. We also did one in Rwanda, in Italy, and we were supposed to do one last year in India, but it got cancelled because of the coronavirus situation. So what are the challenges for women in physics? One thing I've become very aware of is that men support each other a lot, sometimes through informal networks, like they go out drinking after work, etc. And this isn't just socializing, they also talk science in these meetings, and they give each other advice about how to rise in their careers. And women are excluded from this either because it's socially unacceptable for us to go out drinking with them, or because we have family responsibilities and we just don't have the time to join these kinds of meetings. So the aims of our workshops are to give women a space to share their experiences, acquire skills to rise in their career, and form a community that can support one another. So in these workshops, we have little modules. For example, we have a little workshop on how to give talks. So all the women give just 1-minute talks where they explain the science that they're working on. We have a drama therapist from Bangalore. Her name is Maitri Gopal Krishna, and she uses techniques of drama. She's a trained counselor using drama techniques to help women deal with the conflicts and tensions in their lives, like it might be the conflicting pulls of family and career, or it might be a hostile situation at work, colleagues who are mean to you, or it might be something like sexual harassment. And these are very powerful sessions that we have. We have very famous women physicists come talk to us. This, for example, is Jocelyn Bell Burnell, who is very famous for having discovered pulsars when she was a PhD student. And her advisor refused to believe her that she'd made the discovery. But then afterwards, of course, the Nobel Prize was given to him and not to her for this discovery. And for many years, her contribution was kind of ignored. But recently, it's been acknowledged. And a couple of years ago, she was given the $3 million breakthrough prize for this discovery. We had talks by, for example, this is Setsuko Tajima, who is a Japanese physicist who dropped out of science when she got married and had children. But just one day a week, she would ask her mother-in-law to look after her children, and just for the joy of doing physics, she would do experiments in the lab. And after many years of doing this, the person whose lab it was said, you know, you've got enough results now that you can write it up as a PhD. And then she went on to become a very famous physicist and is now a professor in Osaka. This is Sosina Haile, who's a very famous physicist in the US. She grew up in Ethiopia. This is Rabia Salihu Said, who overcame very many personal challenges. She has 6 children, 2 of whom have serious health problems. But despite that, she did her BSc, her MSc, and her PhD. This is Ivana Vobornik, who escaped from the war in Bosnia by crawling through a tunnel and went on to become a physicist. This is Shazreen Mohammed from Zimbabwe, who again has a very remarkable personal story. I think I won't go into it because of lack of time. So at these workshops, women really seem to benefit a lot from the sharing of experiences and from learning all these skills. We also talk about how to write papers, how to write grant proposals, things like that. And at the end of it, we ask them, what do you gain from this? And one thing they all gain is this feeling of togetherness, that it doesn't matter where in the world we are from, but we all have the same problems and we can share our problems and find solutions together. A lot of women have a problem with self-confidence, so we get a sense of self-worth. And very importantly, often because we are such a minority, women in science feel alone. But from these workshops, you get the feeling that I am not alone. Okay. And this, for example, is from the last such workshop. You can see that everybody's smiling, there's a lot of positive energy. And one of the participants in the workshop said, sometimes I think that I'm alone, but this workshop is a good antidote to that feeling. Participants at the workshops, for example, this is Aarti Kashyap from IT Mandi and Zipporah Mutui from Kenya, and they met at one of these workshops and then they started working together. So Aarti essentially supervised Zipporah's PhD thesis, and they have now written 4 papers together. And we still keep in touch. Like this picture was taken just this past weekend. Many of us meet on Zoom and we share our experiences. You can see me here now in my present avatar with white hair. And, you know, these two are from Philippines. She's from Nepal. She's from Georgia. She's from Nigeria. She's from Indonesia. She's from Cameroon. She's from Iran. And we all meet and talk about our experiences. I also have similar Zoom meetings with all the women who have been through my group in any capacity, who were my PhD students, who were my postdocs, who were my summer students. This is a picture of one such Zoom meeting. Some of them are even women who have been forced to leave my group due to family circumstances, but we still talk and support each other and we share our experiences. And so I think this is something nice that women can do, even if we're all spread out across the world. We just talk together and talk. And a very common theme is the, you know, conflicting pulls of family and career. And the advice I have for all of you is whatever happens, don't give up. And I want to end with this quote from Arundhati Roy, which is that I like this quote. She says, another world is not only possible, she's on her way. On a quiet day, I can hear her breathing. So I want to tell you all that, you know, better days are almost here. Things are getting better all the time. And I'm sure that we can all also contribute to making the environment better for all of us. And especially for the men in the audience, I want to tell you that it's very important that you also play a role in making things better for us and changing the environment for women in science. Women alone cannot make this change. It's important that men also contribute. Thank you very much.
Thank you, Professor Shobana, for elaborating your journey from Mumbai to Harvard and back to Bangalore. It was truly inspiring listening to you, ma'am. We have a couple of questions.
Yeah, sure.
One second. Dr. Kalaivani from Mangayakarasi College for Women, Madurai. Her question is, what is the difference in the functioning of walking platinum and rolling platinum?
What platinum and what platinum?
Walking platinum and rolling platinum.
Okay. I mean, it's not different in function. We needed to find the mechanisms because we wanted to find out the diffusion barrier, that is the energy it takes for it to move across the surface. And this is important. To do that, you need to find out the mechanism. And this matters because nowadays we want to use very small nanoparticles, for example, 3 atom or 1 atom or 4 atom as nanocatalysts. And when the problem is that these small nanoparticles are not energetically stable, and it always is energetically favorable for them to diffuse and join together to form larger nanoparticles. And this is called sintering, and this means that the catalyst degrades. So in order to see how likely it is that this process will happen and that sintering will happen, you need to understand the process by which these nanoparticles move across the surface, and that is why we studied it.
Thank you, ma'am. Next, there is another question by Bibi Mary Francis. What are the opportunities given to women in India?
Okay, that's a very big question. So I don't know where to start. So I would say that in India, okay, by law, first of all, we have good policies, we have good laws. I mean, men and women are equal. For example, we have, if you have the same job, you have the same salary. You may be surprised to know that this is not true in many countries. In particular, in the US, if you're in a university, your salary is not fixed. Each person negotiates their own salary. And so very often it turns out that men get paid higher salaries than women. Whereas here, this is not true. I mean, we get paid the same salary if a man and a woman has the same job. But of course, there can be discrimination, there can be disadvantages. I think what we find in India is that there's a big drop in the percentage of women in science after the PhD. That seems to be where we lose the most women. And this seems to be largely due to personal circumstances. Women get married, they have children. And I'm sure you are all aware of the women scientist schemes of DST and DBT, which are specifically tailored to bring back women who've had a break in career. And again, we have very good policies. For example, we have this rule that organizations have to have daycare facilities on site, etc. But they are not necessarily enforced. So our policies are good, but the implementation, I would say, is not always as good as it should be.
Yeah, thank you, ma'am. And one more question from Monica Anand. What would you say to the policymakers in India about low women representation in science? Despite many women-centric programs, why do we still have such low percentage of women in science?
Okay, Monica. Hi, Monica. This is a very complex question. I think in part, people may not be genuinely convinced that this is an important problem, I think. I think there's a sense of complacency. I talk a lot to men, sometimes men in high positions, who really feel, first of all, that India is doing very well. Like I often hear them say, oh, but in India, we do so much better than other countries when it comes to women in science. And they're truly shocked and they don't believe me when I say we have the 6th lowest percentage of all the countries in the world. So I think many of them don't even realize that there's a problem. So the first thing is to educate them that this really is a problem. I think that is the first thing I would tackle. And they are doing various things, like there's this new effort, there's this new program called VIT, which is meant to rate institutions according to how gender inclusive they are, according to how women friendly they are. It is just starting. They have just asked for applications to be involved in its pilot program. I think this program has the potential to be very good if it is taken seriously by everyone and it is implemented in a strong way. Let's wait and let's hope for the best.
Thank you, ma'am.
Good morning, Dr. Shobhana.
Yeah.
It was indeed a very exciting talk to listen to, especially the way you described about your mother, that she did her 2 PhDs after a long gap. And we could personally, I could connect to a lot of the stories that you said, especially your 10th and 12th classes where you felt very lonely and all that. I just have one thing to ask. When I saw your presentation, I could see a lot of inclusivity, like people from different countries. You're doing a workshop with a lot of women from different countries and different. There's a lot of inclusivity. Do you think that a network like Ethana Swan, like the Scientific Women Academic Network in Britain, so something like that would be more efficient in India?
Yeah, so that's exactly what this project Gati that is starting is. It is modeled on the Athena Swan program. Okay. And it is being advised, I believe, also by the people who run Athena Swan. So just Google Project Gati. It was just started about 2 months back, I think. If VIT didn't apply, you're at VIT, right?
Yes, yes.
So if VIT didn't apply, you should keep track and make sure they apply next time.
Okay, thank you, ma'am.
There was some question from somebody in the chat box saying she didn't get the Women Scientist scheme and didn't get funds. So I don't know if she means that she wasn't awarded it. Sometimes it could be because people don't know how to write a grant proposal in a professional way and how to present themselves. So this is where I think the kinds of workshops we run can help, because we give advice to women on how to write grant proposals, how to write papers, how to project yourself, how to give a talk. So, for example, if you run a mini workshop on these sort of soft skills, because these are things that are typically not taught to you, you're expected to pick it up from your mentors and your peer group. And women are often more isolated than men, and it is harder for women to pick up these skills. So having a workshop specifically for women where these topics are dealt with, I think can help. Hi, Gargi, thanks for your comment.
She's in the participant.
Yeah. Thank you. I once again thank Professor Shobana for accepting our invitation and for placing our presentation. Thank you.
If the chat could be saved and sent to me later, it would be good, because I couldn't read all the comments while I was speaking.
Yeah, we'll send it to you, ma'am. Yeah, I think Dr. Geeta, ma'am, please, ma'am.
Yeah, thank you, Dr. Shobana, for your amazing talk and taking us through your academic journey. I have 2 questions pertaining to the science and one for general. It was amazing to understand, to see your work on this iron and gold formation of the alloy and ruthenium. What was the science behind it?
So the science behind it, I mean, why it forms is that, first of all, it's a question of dimensionality, that if you have 2 dimensions rather than 3 dimensions, the physics changes. And we found that what happens, why it is favored in 2 dimensions rather than 3 dimensions, is that in 2 dimensions, if every gold atom is surrounded by iron atoms, this allows the iron atoms, sorry, it's the other way. If every iron atom is surrounded by gold atoms, it allows the iron atoms to be less hybridized and therefore to have a higher magnetic moment. And this lowers the energy. So it is the magnetic exchange energy which favors the formation of this alloy. And it is because it has, in 3 dimensions, this doesn't happen. The other thing, what the role played by the ruthenium is, it's a sort of template which fixes how far apart the atoms are. So it also matters, so it's the geometry where every atom has 6 neighbors and how far apart they are. And it's a magnetic exchange effect. If you just send me an email, I'll send you the paper.
Oh, thank you. And so interesting that you're exploring different materials. I mean, is there any work by you on materials in nature? Because nature is the best.
No, I haven't actually done any work on that. No.
Because yesterday I was listening to from a talk from an European on materials, and basically how nature materials plays a major role.
Yeah, I mean, a lot of people work on biomimetic materials and things like that, but
Like
I
just
haven't done
observing
anything.
the nature and developing materials, I think that's very interesting. So I thought
Yeah.
if you have explored that area. In general regarding women, and I think though we are very, very less in India, we should stop differentiating ourselves in men. I don't feel if I'm sitting with I have 50 men, I don't feel I'm only the women. So that kind of feeling should come in a woman to be more outward going. That's it, okay. But what I feel is women.
I just want to say there that, you know, it's, I mean, I don't think we should put the onus on the women to say they shouldn't feel that way, because some women do feel that way and some men do also feel uncomfortable. I mean, I've been told by men saying, oh, I feel uncomfortable because you are here. It means I can't talk freely and things like that. So you shouldn't put the responsibility, in my opinion, on the women to say you should feel comfortable being the only woman. It shouldn't happen that she's the only woman. That is what we should change, I feel.
Okay, and I feel even the women have the passion and perseverance. They drop at some moment. They are demotivated by the circumstances. I think that's the only challenge women are facing, in spite of their passion and perseverance and doing better than men at times. The demotivation which makes them to get out of this. And the second I feel is the family, as you said rightly. They feel guilty for either they are unable to contribute 100% like other women in the world. So that these are the two factors I feel the women are like bit lagging in their performance. Am I correct?
Yes, but I feel again, I mean, one shouldn't put it in a negative way. Anybody would get demotivated if, I mean, these are really hard circumstances. I mean, it just seems so unfair that for men, it doesn't necessarily seem to be a problem to have a family and a career, but for women, it is a problem. And I mean, the demand being made of women is that they should spend 100% of their time with their family as well as 100% of their time on a career. And nobody can do that. I mean, it's just physically impossible unless you have a time turner or something like in the Harry Potter movies. And so it's inevitable that you will feel guilty that way. Either your colleagues will make you feel guilty or your family will make you feel guilty. And so the only solution, I think, is that the men have to share in the housework so that the woman doesn't have to do all the housework. I mean, there have been many surveys and of how much of the housework is done by the women, and both in developed countries and developing countries, most women say that they do most of the housework. Women scientists say that. And unless men also share it, it is not going to be possible for women to succeed in science. So I think some of this burden has to be taken up by the men, I think.
Yeah, true. But I think time is slowly changing, and as you said, like you conveyed the message to the men audience over here.
Mm-hmm.
Each other's support is very, very important for either of them to grow. Thank you, Dr. Shobna.
Thank you.
Yeah. Thank you, Geeta ma'am. So thank you once again, Dr. Shobana. It was really
I just noticed Pratibha Jolly is there. Pratibha, do you want to say anything about Gati? I mentioned Gati.
Yeah, hi Shobna, and
hi.
I'm very happy to be speaking after you. And yes, indeed.
Because I was asked some questions about Gati. You'll be talking about Gati?
I will not be talking about Gati today.
Okay.
But I'm very happy that it's been launched. I will maybe make a beginning and put some comments towards the end. I'm really, really happy
because
that.
okay, good, because I got some questions about it. So
So it depends on the on Nirmala, and I'd be very
Yes,
happy
yeah,
to just talk about Gati and extempore then, depart
Oh, sure.
from my prepared talk. But since Shobna has asked, let me say gender advancement for transforming institutions is what India has launched. DST has launched, and I and a small team are developing the framework for a very innovative assessment process, which is reflective and action oriented. So we are going to begin with 30 pilot institutions, and there's been an overwhelming response. We've had more than 160 institutions applying, and I think that's a good start. Though it's been said that it's modeled after Athena Swan, it's not really going to be modeled after Athena Swan, although we have British partners. And as Shobna's talk has very clearly indicated, India's policies are quite different, and the challenges the West has is very different from the challenges India does. But there's a universal common denominator across the globe, and that is the obvious bias and that women in science face, women in general face, but in science particularly. And as again Shobna said, the percentage of women in higher academia and research is dismal. We really have a lot of catching up to do. So we hope that the reflective, collaborative process that Gati will have to offer will be a game changer. But it's a community project, and it is for all of us to come on board and look at what is happening in our institutions. And I believe that this decade belongs to us, because it's not just a moral imperative, but it's also that today the environment is more sensitive. And rather than, it's not about saying why is it that men behave in a particular way, but to launch a dialogue and have a sensitive cultural ecosystem transformation. So it's really tough, and it has to happen on the ground. So Shobna, you've been a leader in this, and one is really looking forward that we will have a very vibrant network of women. You need to be seen, you need to be heard, and then I think we'll carve our place. That's very important. So I've also launched an informal group called iSwan on LinkedIn. And I invite all of you to join, because here is a huge opportunity to create a database which you can keep updating. You can keep updating your biodata. So, to find all of us on one platform, if somebody is looking for a particular kind of expertise, it helps. And also the hand-holding will be enormous. So I hope that Nirmala is very much on it, and she will send out an invite. And we can begin a dialogue on social media, but a professional networking site where we also can build our biodata for others to have a look at. I think as I go along in my talk, I'm going to talk about how we build these communities of practice, because somehow, I just want to be forward looking, and the challenges are there, but it is for us to bounce back, each of us. So Shobna, with that, Gati is very much on, and I look forward to your continued support and collaboration on it.
Thank you. Yeah, thank you, ma'am. So with that, I once again thank Dr. Shobana for such an interesting session on women in science. Thank you, ma'am, for accepting our invitation and gracing this occasion. Thank you. Yeah. So with that, we'll move on to the second talk for today's session with Dr. Pratibha Jolly. Ma'am, this is Nirmala. Good morning. So thank you for accepting my invitation and accepting for giving a talk. So we'll start the session with Dr. Pratibha Jolly's talk. May I request Dr. Vimala to introduce Dr. Pratibha Jolly.
Thank you, ma'am. I'm happy to introduce our next speaker, Dr. Pratibha Jolly, former principal of Miranda House, University of Delhi, India. She is an enthusiastic educator promoting creativity and empowerment. Dr. Pratibha is the ex-principal of Miranda House, the premier college for women at University of Delhi. She obtained her PhD for the theoretical work in chemical physics from the University of Delhi and taught in Miranda House for 8 years before joining the Department of Physics at the University of Delhi as a research scientist. Dr. Jolly was awarded the Kilambi Ramavataram Fellowship by American Physical Society, Tata Fulbright Travel Fellowship in 1995, the prestigious Fulbright New Century Scholar Award 2009-10. She was also an expert member at National Assessment and Accreditation Council (NAAC) General Council and Executive Council from 2017 to 2020, and currently she is the academic consultant of NAAC. She has also received the Australian Leadership Award Fellow in 2013 and the GIREP International Research Group of Physics Teaching 50th Anniversary Medal in 2016. Her area of research includes computational physics, electronic instrumentation, use of computer-based technologies in education, cognitive aspects of students' learning, and diverse student population. Now, may I request Dr. Pratibha to deliver her talk.
Thank you very much. And I seem to have already begun the dialogue. So let me share my screen and let me know if it's working. Hi, it's a pleasure and thank you very much that on this International Day for Science for Women and Girls, you have invited me to give this talk, and I expected that many of us do speak about the deficit that women face when they make a life in science. So I thought that instead of presenting that data, I will share my own journey in science, and more importantly, like many of us, we do feel that we're going to continue in research, but sometimes circumstantially other things happen. And I, due to certain circumstantial forces, did not really pursue my interest in research, but I got caught in education. And this is my story. And I'm going to talk about largely my life at Miranda House in an administrative role as someone who was trying to lead an institution, and in particular make a change in the scientific achievements of women, and this being a women's institution. So I'll talk a bit about decoding a legacy of a well-known institution and what stakeholder expectations are, and what kind of challenges one has to always overcome and create opportunities. We also speak about incremental change and disruptive innovations that we launched, and most importantly, about building a community of practice and establishing distinctiveness in institutions, establishing a brand value. I'll also talk about my life in science education and the innovation and transformation I hope we have been able to achieve. That's really been through designing active learning environments, my work in physics education research and research-based pedagogies, my passion about early introduction of appropriate technologies, which doesn't really mean always computer-based technologies, though those, of course, play a very important role. But more importantly, how one is able to become an agent of change through action research, and how every teacher can effect that change in her own laboratory or classroom. And as I said, building a community of practice is what has been my passion, and I do think that's a mission that found me. And if time permits, I'll talk about my own work with international communities and mainstreaming of best practices and those collaborations. So let me begin with the story of my alma mater, Miranda House, a premier institution, a legacy of excellence that it has, established in 1948. It is certainly it chronicles the history of women's education in India through its liberal arts and basic science programs, very strong on humanities and social science, but equally having established basic sciences way back in 1948 as honors disciplines, it has achieved quite a lot. And it's a large institution with about 4,000, 5,000 students, which would be size of a university in many of the global globally, the universities tend to be that size. But in India, we have larger institutions. So as I said, established at 1948 by the then Vice Chancellor Maurice Guire, there was a mission that was given to the institution, which was to nurture women. And the founding faculty were hugely steeped in idealism and committed to women empowerment, to giving a voice to women. And that is why I think a large number of women from Miranda House have done rather well. They have been global leaders and nationally are very well recognized. So there was a huge emphasis on rigorous academics, but discussion and debate, to be able to voice your opinion. Or in fact, to do that, one had to form an opinion. And therefore, because creative pursuits and soft skills always took center stage. And the individual was always important. So the faculty-student relationships were very, very nurturing and strong. And before it became fashionable to talk of diversity, it was a living experience in an institution such as Miranda House. So engagement with community and the real world problems was a defining spirit of that institution. And you witness it through his famous alumna, be it the 3 times Chief Minister Sheila Dikshit, or novelist Anita Desai, or Meera Nair and Nandita Das, or Anjalila Menon, the economist Bina Agarwal, and a woman of many parts, Shobna Narayan. They've all raised the bar. And, if you look at when they move from Bollywood to Hollywood, they've always tackled very complex subjects, such as Sonali Bose has done through her films like Margarita with the Straw, or The Sky is Pink, and so on and so forth. So the challenge for such an institution is to keep that, sustain that excellence. And, if you look at the Padma Awards, almost every year a Mirandian has had it. And, they've had the Padma Bhushans, or they have the highest literary awards, or Sahityakala Academy Awards, and so on and so forth. So much celebrated. Anjalila Menon also, has been celebrated as an artist, and so on. However, what is important to remember, and Melinda Gates really puts it very beautifully, a woman with a voice is by definition a strong woman. But the search to find that voice can be remarkably difficult. And so how is it that institutions give that voice to a woman? And how is it that that voice is often very strong in the arena of social science and humanities, but the voice and the life in science is not always recognized to be equally strong, and the potential is not celebrated as much as in other disciplines? So the institution is obviously close to my heart because I was a student there. And my journey here is also one of both frustration and empowerment. Because after my PhD at Delhi University, and I had at that point, due to personal reasons, dropped the idea of going abroad for a PhD. And I found the whole program extremely frustrating. And then I joined, I got a job. And so I said, okay, 1 year later, I'll fly the cuckoo's nest and take on a postdoc. But then when I started teaching, I found it so frustrating, especially the lab, the cookbook approach, and so on and so forth, that had to sit back and I had to think, what do I do? Because I have no faith in the traditional classroom. And that is when I launched with DST support at hardly 50,000 rupees in 1984, a program called Learning Through Investigative Projects, the flavor of research. And I came from a theoretical background, and learning to work with my hands, with students, to fabricate equipment which wasn't available, to learn electronics and so on. And obviously programming came very naturally to me. And as my story will unfold, you'll see how we then evolved our programs to start integrating the technology, and both learning to work with my hands and to procure those components and things, running to Chowri Bazaar or to electronics markets in Chandni Chowk was an experience in itself. And I was often asked, do you run an industry? How come you're buying these things? What kind of a business do you have? And I said, oh, I'm just a teacher. I'm just building things for my students. And with that said, I took an opportunity in 1988 to move out of Miranda House, where it was always, my colleagues said, okay, so don't do the routine experiments, but we had introduced compulsory project work in this thing. Take all the projects. And so I was doing at that point projects and project-based learning with all of the third year class of both Miranda House and St. Stephen's College, where I had a collaborator. And I took this opportunity to go to Department of Physics to create a non-formal program, a lab of my own for undergraduate students, largely women, but not necessarily only women, because students from other colleges also kind of flocked and worked beyond their classroom hours to get a flavor of research, to do small science. And some of them have moved on to doing really big science and are much celebrated in some of the premier institutions in the country and abroad. When I was, I really enjoyed it. And in 2002, I was suddenly pulled out by my vice chancellor and said, go and become the principal at a college I'd never heard of. And, I kind of said, if someone asks you as a leader of a team and you don't take it on, then you lose your right to criticize the education system. Because he said, take the college as your laboratory. And it is time now to implement and mainstream and scale up all those innovative things that you've been doing in your little lab that you call as lab of my own. And for a theoretician to have that lab of my own, work with their hands, just be a few steps ahead of students, was an incredible experience. And there I was, trial by fire. And in 2005, Miranda House summoned me and nudged me to apply for principalship there. And I had survived for 2 years in the other college. And so there I was at Miranda House. So back to Miranda, finding my mission and trying that. My passion was science education research, working with students as replicating a grad school experience for undergraduates and developing innovative labs. And working also in that process, sometimes in creating a very, very novel faculty development programs. So here I was, and this became the story of my life. And I never did go for my research as I had planned, because this unapologetically took up 365 into 24 hours. And it was such fun because they were young, bright students to work with, and a gold mine area, because anything you want to look at in education is wrong, and you can attempt to do things differently. So it was fun. And when I came in, I knew this was going to be another trial by fire, because the college had not had a principal for 5 years. There was an acting principal. Infrastructure of a heritage, beautiful Walter George building was completely degraded. The gate was crumbling, the boundary was crumbling, there was no pathway, it was waterlogged, and the old beautiful red brick building was crumbling. There was academic stagnation, not because the faculty was not good, but because of a sense of complacency that we do it right. But when somebody comes comes from outside, you know that others are doing equally well and there is no pecking order. And this is something to realize that, every day there is something new that can be done. You need to reboot, you need to reinvent yourself. And you need to reboot and reinvent because societal changes are taking place, technical changes are taking place in a very good way. And you'll have to forgive me for a minute because I'm by myself and I need to just quickly. So sorry. So some challenges of working from home. So there are new ways of knowing, learning, and sharing the new skills and instruments. And obviously, education cannot be isolated from the changes that are taking place around. But somehow, education tends to be static. And these changes in times and goals have set for the country globally for all aspirational nations, innovation as a new mantra. Whether we look at digital India, we look at renewable energies, we look at the Make in India, or we look at the mobile penetration in the country and so on. So things have changed and they were changing right at the beginning of the century when I took over. So importantly, however, yet if you look at one size does not fit all in a diverse country, you have the elite institutions, but you have people coming in there who come from a challenging set of backgrounds, and sustainable development goals are very important to provide education and an identity to everyone. So the aspirational nation on the move today looks at equity, excellence, and expansion. The demographics is changing and the vocabulary is changing completely because we are better networked, we have the digital transformation. And if you look at institutions that are considered as elitist, such as Miranda House, today 70 to 80% students come from outside of Delhi. Many of them are first generation learners. They have challenge of language, but they have made it to the institution on their own merit, meeting almost 100 on 100 baseline entry level marks. And they are looking for carving a new identity. So this changing demographics makes it a moral imperative that we relook at how education is to take place and how we are going to nurture them. So we have to meet the diversity and inclusion challenge, create a sense of identity and belonging, and help these young women who come into education develop a global perspective. And it is important, therefore, that every institution should develop a diversity intelligence, which unfortunately does not come naturally to us, even though we have a very diverse country. We have to impart to the millennium bonds what are called the 21st century skills of critical thinking, problem solving, wean them away from rote learning and the kind of exam system that they have grown so used to that allows them to get 100 on 100 and reach higher education, and help them build a life and a career in a world which is today called the VUCA, which is volatile, complex, uncertain, and ambiguous, because we do not know what skills will be needed in the future, what the future of work will be. At the same time, we have to help these young women move from the low tech to the high tech, move beyond just having micro hopes or micro ambitions or, doing things on micro scale with small amount of money and set up a small business, a micro venture. They have to think big. So we have to give to them aspirations. And this is what institutions such as ours like to do, help girls and women break the glass ceiling and do it unapologetically. To do that, therefore, it's important for us to understand what is the disruption that is happening, what are the disruptive changes that are coming in society because of the technological advancement, and how education is lagging behind, and how we really need to, therefore, not have incremental, small, linear changes, but look for the 10x, the exponential change. And which really, if you look at how things go, and this curve is also something on which I have ridden in my personal journey for science development and so on, that when you look at initially you digitize things, it seems very deceptive, it's very slow, and you feel nothing is going to take off. And that's the story of my work of about 3 decades, that it was ahead of its time and no one was willing to look at computer-based, sensor-based measurements and so on. They say, oh, lovely work, but it's never going to come into the classroom. But then suddenly it becomes disruptive. And you can see how during COVID time, it has really, it was already accelerating, but it has been accepted today, and how we have all ridden on this accelerating exponential curve to redefine hybrid campuses and our learning. But in society, we have witnessed how today we have kept alive because of during COVID, because of demonetization, everything. And I was suddenly disrupted because there was a delivery from Amazon, and things have dematerialized because you use and they democratize. The data is everywhere, so Ola will have no taxis of its own, Oyo will have no hotel of its own, and so on. And data is available, knowledge is available much easily. So AI, the big data, machine learning, deep learning, these are the new mantras that are coming, and without this, it is going to be very difficult to establish either learning or venture as we go out in our career. So for today's generation, it is the moonshot generation, terms which have been coined rather intriguingly and beautifully. And you have these challenges whether NASA or that wonderful Elon Musk will float. And even today's paper has, you may have 100 million or a 10 million award for a private group of students to land on the moon, which is what an Israeli team did. And they crashed, did not have a soft landing, but they still, instead of the 10 million prize, got 1 million because of the impact that it made on STEM education. So the new generation is challenging the status quo, or we want them to. We want them to address the global challenges, be it climate change or be it energy crises and so on. And we want them to accomplish the incredible. We want to motivate our teams and students in particular to think big. We want to frame for them problems as solvable. We want to focus their attention on how to solve challenges and create a culture of innovation, and anything is possible. And this must begin early. It must begin in colleges and schools as it goes. And in fact, if students are taking on these big problems, you have the youngest, say, 7-year-old as making robots and so on and giving TED Talks, they are capable. So I'm involved with the International Science Engineering Fair, ISEF, and we've just finished selecting the team of Indian team to participate in this fair in US, this time virtually. But last year you had Karthik Ramesh winning a $75,000 award for developing spinal surgeries complete package based really on how the Pokemon game works and using augmented reality. And in the winning team were also 3 other women, and 2 of them happened to be people with Indian names. So catching them young has become the mantra. And you would have heard about the 3M and Discovery Education Young Scientist Challenge 2020, where Anika Chibrulu researched on a molecule that can selectively bind on a spike protein to find a cure for COVID-19. So fostering next generation of science leaders is becoming extremely important. And these students are doing well on their own, encouraged sometimes by families, but also in cultures where universities and research institutions reach down and build bridges over which the young can walk across to their labs. And this is something that we need to do in India. Today, the Time this year carried the Top Innovator Kid of the Year 2020, Gitanjali Rao, who has several innovations to her credit. detecting lead content in water using nanotubes, or opioid addiction early, or detecting cyberbullying early, and so on and so forth. And before this, she had also won the 2017 3M Young Challenge. You have teen entrepreneurs. Here is Nikia, who's worked on early risk detection of oral cancer using biomarkers. And this year's IRIS National Fair winner, just about a week, 10 days back, is Jui Keska from Pune, who's worked on a wearable device for Parkinson's disease and solving problems close to her heart. But my heart goes for school kids of Aurangabad Municipal Corporation School, 6 girls out of a group of 10, and their satellite was part of the 100 small sats which were just launched under the Abdul Kalam Space Research Payload Cubes Challenge. So anything is possible for this moonshot generation. We owe to give it to them a great nurturing environment, both boys and girls, men and women, but girls in particular and women in particular. So there's a huge paradigm shift, profound change in how we view education, or they should be. NEP talks about it, but how we are going to implement it till the last mile or the last educator does not view this change or have a DNA rewired to look at the change that is required. An educational institution does not exist to provide instruction. It exists to produce learning, to help its community learn to learn. And this kind of a change is going to make a significant impact on higher education, its structures, functions, and outcomes. And some of us who have worked towards it know that this is a challenge with always shifting goalposts, because the world around you keeps changing, the technology keeps changing, the generation changes, the demographics changes, and the disconnect is something which is in any case difficult to bridge. And on top of that are social aspects of diversity, of learning difficulties, and so on and so forth, which are not understood at all. So these disruptive changes in higher education ecosystem, with influx of new technologies, diffusion of new pedagogies, which all of you have experienced during COVID, the naysayers have also onboarded those new platforms and understood what the modes of learning are and how they are challenging. And that we have experienced the democratization of data, because so much has been made available free, whether it be Coursera or whether it, any nugget of knowledge or educational resource or any resource. Today we are homebound, we are delving into it. And so today these words are better understood. And with this, however, in education, we also need new frameworks of accountability and new models, not just of business, but also in any sector. And it's not going to happen always with ease. Sometimes you've got to push, sometimes you've got to pull, but change must occur. In fact, it's not going to wait, and therefore expectations and institutional aspirations will now be driven also by those of the young students, but also national aspirations, societal aspirations. And what is important, therefore, is that our work in institutions, both education and research, should have a social relevance, and the student should be at the center of it and benefit a lot. So today the country is helping us, governments are helping us to nurture the startup story, the Atal Tinkering Labs in schools, the Atal Mission with incubation centers, the challenges of smart hackathons, and area which VIT, I'm sure, must be participating in, and so on and so forth. So much is happening, but yet hardly 10% of startups are that of by women, though 90% of the startups are for age group less than 35. And it's important, therefore, that we should also consider how we can help our students not just be scientists, but also have a component of enterprise education so that they can become entrepreneurs. Because I do think that the boundary between whether you are a scientist, a tinkerer, an innovator, or entrepreneur is fuzzy. And when we create these kind of boundaries that those who are in education or in enterprise or in corporate or industry are not really doing great science, we are doing a disservice. Because blue sky research and the frontiers research is as important, and so is technology and how we are able then to send somebody on the moon. And it's important. And women are leading, as was in the previous talk mentioned. ISRO's women and those in DRDO are really leading lights. So successful scientists and successful entrepreneurs share many traits and attitudes and skills. And you never know when you're going to step from one boundary to being another, when you will view this photograph as a young, beautiful woman or as an old person. So since basic science underpins technological innovation, strong fundamentals in science is important, but also capacity to work with your hands and have a translation of the work that you do. So product development in any project work is important. The other foundational skills are those that scientists in particular need to have, which is the art of argumentation. The science and art of argumentation, basing it on evidence, is extremely important. You can see how GM crops are still not launched in the country because, evidence-based science, we have not focused on. We have not focused on communicating our research and so on. And the greatest challenge in all this, therefore, is of mindset, of changing from a fixed mindset to the growth mindset. Therefore, it's easy to say think out of the box, but actually there is no box, because when you look at it, creativity is boundless. And we have to therefore give to our students many skills, an open mindset, but in particular, today for women, enhancing spatial data visualization skills is important. To be able to work together is important. And, graphing, modeling, simulation, video games. So it's been such fun to encourage our students and to give them facilities to do exactly all this in the institution, because families are not going to come forward and do it. So design thinking is what is needed now to unleash institutional innovation with empathy. Allow students to ideate, to make prototypes, to test and implement them, and explore unlimited. And I think this is what my mission has been. Because if education continues to advance one step at a time, we will fall exponentially behind the world for which we aim to prepare the learners. And that world is today using what are called as disruptive technologies, accelerated technologies, the exponential technologies, change 4.0. As I have said, education is the hardest sector to reform and to reboot. And with this understanding that I developed, working with young students early enough, participating in National Children's Science Congress, IRIS, my own lab of my own undergraduate students, and so on. Here I was thrust into an administrative role, and therefore, brick by brick, resurrecting a beautiful heritage building, and project by project, I said, let the role fit me rather than I fit a role of what it means to be a principal. And it was a wonderful thing that instead I started dabbling with stone, brick, mortar, wood, glass to restore the heritage building, and a lot of engineering, and actually 90% of the time going on the drawing board to do all that. But more importantly, not just rejuvenating for the millennium, the institution, restoring its past glory, and creating state-of-the-art infrastructure, but establishing what would be the future of the classroom, the interactive learning studio, where you really have to do away with the traditional lecture and the laboratory and be able to integrate it all into a learning studio and an experience, like, let us say, the MIT's technology-enhanced active learning environment. But before that, though MIT would say it's the one that started it, a lot of collaborators have from the 90s established workshop physics or studio physics and so on. So there have been many avatars. And we have been able to establish that at Miranda House. And now some ICERs are going for that. But this is a story right of around 2005 when we did it, but not in a mainstreamed classroom, yet in a project-based environment, because it's difficult to break the mold if you are a constituent college. So capacity development has been important, and one has learned it in the context of what works, what doesn't work, and especially for women students. So from education to research and innovation, and keeping in mind that we live in a world where diversity and demographics requires that we carry each one along with us has been important. So this picture of sustainable goals on a big, beautiful red brick always is a motivator for me, with a student coming and says, ma'am, you know what, I'm going to devote my life to this particular goal. And that is what gives you the greatest satisfaction. So learning together anytime, anywhere was our USP. Even though we had state-of-the-art and Wi-Fi campus and so on and so forth, but building a community of practice was important, with teaching, research, extramural, and linking academia to both society and workplace that I've been talking about. Facilitating and empowering the faculty is most important, and largely women teaching faculty was very important. And that one did with game-changing practices. So early enough, in about, say, much before it became fashionable, we issued out netbooks to all faculty with no questions asked. No question asked at all, and at their own pace suddenly, and that pace was less than a year, everybody started using IT in education, and it became a repository of all their academic material and management of academic material, and all meetings went online. Therefore, changing paradigms requires raising the bar. There are many factors that influence success, and breaking the status quo is a challenge. Moonshot thinking is always a challenge, but one can create personal value and competence for all stakeholders. And in an educational institution, it means the staff and the students and the interactions with society as such. And in doing that, if you yet retain the human element, then you're really happy. Because I remember at an NDTV show, one of my students said, the happiest moment is when I sit under a tree and watch a squirrel. And the famous cats at Miranda House, and you know how so many films have been shot there, kind of talk about how creativity is unbound. And even high-tech campus, but with a heritage building, students are so involved. So the canvas for institutional mentoring in a liberal education ecosystem is what works best. And it is large because you have seminars, conferences, workshops, extramural, internships, networks and societies and clubs. I'm sure all institutions have it, but how you leverage it makes all the difference. That said, the real challenge is in what goes on in the classroom. How do you create a thinking curriculum, a thinking teacher, and therefore a creative student? How do you create an environment within the classroom, not just with, sitting under the tree and chatting with friends, that reflects active mental engagement and joy of learning? And that has been my work. So there is the myth of science that you've got to be an Einstein to do well in science. That needs to be broken. And anyway, the real world is not Newtonian. And we always teach them only about what Mr. Newton said and do that only on the blackboard. So that makes learning of science all the more difficult, and it makes it abstract and focus always is on fundamental principles without applications, and problem solving in saying the cow is a sphere because that's what it is for a physicist, and we fail to build the bridging analogies, and that is why a large number of women, even though they want to stay in, and large number of boy students also fall on the wayside. So the challenge is not just gender based, it is also discipline based, and we lose students early enough, and this is not emphasized enough. And I do feel that this is what we need to look at, because today the girls and who are coming in, the women really want to devote their lives to science. But if they fall on the wayside, it's because their early experiences have been daunting, and they are driven away from the science, especially physics. So we were fortunate, we were able to establish the D.S. Kothari Center for Research Innovation in Science Education. Our mission was activity-based science teaching learning programs and research in science education, all disciplines, and capacity building and nurture programs, as well as outreach programs towards school students. So we see that colleges are a bridge between, on one side, schools, on the other side, research institutions, so that you bring in the experts from the top institutions to handhold your students and help you and advise you to do things differently. But how do you make the change? Because there's nothing available in the educational market. There's nothing off the shelf. And that's why right from the 80s, I was developing curricular products. I was forced, even as a theoretician, to develop low-cost, locally produced instruments, because unlike much of the developed world, there wasn't much available. But that was the charm, because it organically evolved, and we made, and we were able to repair, we were able to change, we were able to move with the changes that were happening. And that's how we moved from simple op-amp based instrumentations to computer-based, sensor-based data acquisition systems, and introduced technologies. And that is also why I spoke of the exponential. All our innovations from 1988 was so slow to take off, because before Excel became popular, I had already developed programs to aid my students of that kind. We already had developed a complete data acquisition system, sensor-based, with a software, full packages, which actually DST and TIFAC took to the patenting stage. But it was ahead of its time. There was no startup, and I did not know how to do a startup. And so there we were. And gradually, because the lateral spread was so much, because we were empowering students, it didn't happen. Everyone said, good work, but it is never going to come in the classroom. And today, this is what is the classroom. This is the future of education, and that is the disruption that has happened. And we have to be prepared for newer disruptions to come. So today I say that all the work I did in creating digital resource centers and a computer per student almost is redundant. It is no good, because the mobile is the lab in is my pocket. And using the sensors based on that, we can create for just anyone in the country, and have its diffusion across the country of a lab, a versatile lab in my pocket, because everybody is going to move towards having a smartphone. What's important, therefore, is how to use your technological knowledge and marry it to content and pedagogical knowledge, so that you have the understanding of what is going to work in the classroom. It's not enough to have the content knowledge. It's not enough to use technology, but how to bring it all together is most important. What is most important is to construct new learning environments if you have to have retention in science. And that is to enhance learning with active mental engagement, which is hands-on and minds-on, and which also is hearts-on, because it promotes active social interaction. So today that students have peer learning just because they have a smartphone. And this needs to be leveraged rather than, they should not be, and in hybrid education, we have to certainly leverage these new methodologies and so on. So early professional development of students to help them to build a robust self-image, to learn to work in collaborative teams, not just talk about it, not just wait till the PhD graduate school to give them these skills, to allow them to network, especially with other women, and differentiate personal and professional boundaries, the demands of a job and career. So these are the things that they need to learn early, because this is an aspirational moonshot generation, and we are doing disservice if we keep showing them the data on that, oh, women are not going to be able to do it, the generation before you did not do it, and so on. And so this has to become the norm. And I hope that under the new education policy, enough faculty is trained to be able to replicate what works, what is known globally to be the best practices. And this you can do through collaborative student-faculty teams and peer teams, launch early undergraduate research with a dual purpose of designing and developing innovative resources, and second, the training, task-based, small tasks, as well as open-ended research, and the sky is the limit. And have faculty that has fallen on the wayside, is not able to do research, commingle the role of a teacher, curriculum developer, and education researcher. So project-based learning and cognitive apprenticeship is the thing that I have learned in my life works. Project by project, students then get so motivated that today my students dot the best institutions in India and the world across. And they're far better scientists than one ever hoped to be. And what has worked is like a master potter, craftsman helps someone first to model and then gradually removes the scaffolding and allows free exploration, the whole process of learning to learn. This model works. Cognitive apprenticeship, and this is what we all undergo in a grad school. So modeling, coaching, scaffolding, and reflective processes, and communicating what you're doing, thinking aloud, and exploration on your own is what needs to happen. So these are the pedagogies for global competence, I think, and women in particular have gained tremendously out of it. I have personally gained tremendously out of it, and this is what I end up doing anywhere. You know, I just see a project in anything 24 hours, and that's a story of my life. And group-based project work is really empowering. Structured debate, this is a summary, art of argumentation, organized discussions, and service learning. Engaged institution, engaged universities is what we need completely. And so let us say you don't need always ICT. You can motorize imagination with just, you know, a little bit of stuff, a nail, a wire, a battery, a magnet, and say, what can you do with this stuff? Maybe make the smallest motor in the world. Or you can then move on to more sophistication, not just sensor-based and today tablet-driven things, but also develop your own lab on the mobile, or delve with robotics and tinker, and maybe now today 3D printing and drones and aero modeling. And so these students, from many of them first generation learners, from economically marginalized communities, but aspirational, have made their way through such things. And this is one of my studios. It is designed, the pedagogic design is in its tables. So you turn towards each other as a team, and this is not those linear lab benches, and then you work together. And this is what works. And of course, we have the advanced labs. So as I said, if I have time, I'll take 2 minutes. What helped me was that it was a lonely job, and I was really working almost alone, and I was trying to create faculty development programs so that we would create a critical mass of colleagues who would speak the same language, who would walk the path with me. And it was very, very small. And then I did a workshop where in 2000, it was a faculty development program that ran for a year, where groups of teachers undertook classroom research and presented their data at the end of the year. And they developed a vocabulary for what physics education and its research is. And that gave us the power to hold a critical mass to be able to organize a Physics Education Conference. And it is at that point that I do think that some form of recognition for the work one was doing came about. And it really helped me because it gave us the grant to set up the DS Kothari Center. It also took me to my International Commission on Physics Education of IUPAC that I was asked to chair for 6 years. Normally it is one term of 3 years. And a defining conference that I did with my colleague Priscilla Laws, who's a very renowned educational researcher from Dickinson College. We chaired a conference on physics and sustainable development and developed Educate the Educator programs and active learning workshops and outreach activities for the whole world. We try to develop, especially for developing countries, global partnerships to simulate communities to collaborate on development of quality educational resources and do it in using local materials. So have very culturally rooted, organically evolving packages. And the highlight was a resolution on importance of active learning and hands-on physics education, which was adopted in 2008. And around that time, we were able to launch and motivate. This team has done miracles. ELOP workshop, the active learning workshop in optics and photonics, has traveled to reach thousands of students and a very large number of countries, and similar initiatives in Latin America and so on. So all these collaborations have really helped Miranda House and my own work. And we launched through ICPE the Physware collaborative series of workshops with my colleague Dean Zollman, Elena, and Priscilla with ICTP support. And we were able then to launch these active learning 2-week workshops with as many as 40 people from 20 odd countries with ICTP supporting. And then as it wasn't taking off, I did one at Miranda House, somehow managed to bring in the grants. So 1 week of low cost string and sticky tape, almost experiments with no technology, and then ramping it up to very high technology and taking the faculty through this. So that has been extremely helpful and has changed. So let me say that learning organizations, creating them, creating people to learn collectively and networking is important. And I have been fortunate to be able to get an institution that became a lab of my own. And the place where I started, most frustrating it was those early classrooms. I thought, what should I do so that I'm happy? And I found my joy in creating a lab of my own for students, undergraduate students, and using that for launching innovation. We learned collectively, we networked, and very quickly we found that we had international linkages and we were able to build teams and be future ready for the world of work. And we could do this through smart goals and action plans. And I portray this because Gati was talked about. Gati is going to be about smart goals and action plans for gender transformation of institutions. But this is what will require not just overcoming cultural obvious bias, but to strengthen and give strong fundamentals and confidence to young women so that wherever they are, they can hold their own, and it's important. And it is going to be about mainstreaming global innovations in culturally sensitive adaptations to build community of critical actors or practitioners that share the same vocabulary and have enough regional leaders through intensive train-the-trainer workshops and sustain this capacity building. And I think this is where what's been important. So with that kind of an environment, Miranda House regained its premier standing when we had been the poll star at NRF rankings 4 years in running, the All India Rank 1, sustaining excellence, and that's really been very, very heartening. It's been a good point to retire from that institution on and move on to another challenging project, Gati. And I must say, a journey of 1,000 steps always begins below your feet. And my first international Educate the Educator workshop was in Bathurst, Australia, 1984, when as a theoretical physicist, I started learning electronics to build instruments, nudged by my own supervisor. And it has been a good life because I did receive the ICP medal 2020. Thank you so much.
Thank you, ma'am. Thank you, ma'am, for your informative and inspiring talk on engendering change and transforming ecosystem. We have a couple of questions from the participants. Can I, ma'am?
Yes, please.
One is Dr. Joy Sophia Pondraj. What are the possible fundings available to implement or support educational plans in India for NGOs as well as implementing innovative research models?
So as I said, when I began 1984, I got 50,000. It was, I think, amongst the first projects that was financed by DST. And after that, both DST and UGC have supported me. In fact, I got my UGC research scientist post, which I used for 15 years with a supernumerary post at Miranda House. To launch integration of ICT in education and develop all my work, which I've described to you before I moved to Miranda House. Today, DBT has a Star College scheme. Just yesterday, we were selecting other institutions to come on board. And with that, institutions have got crores of funding to, improve the curricular material, and in particular teaching in labs. So Star College DBT scheme has been a very empowering thing, but DST itself today has large number of grants. So UGC minor research projects are there as well. You can look at it. But what is important is that there are large number of opportunities that are now coming. And if you look at schools, now, Atal Tinkering Labs schools will have the corporates hand-holding them. IBM has launched Women in STEM nurturing program. So, everybody realizes that the talent pool that we have in the young students needs to be nurtured. And that educational institutions are not going to be able to deliver on their own. So, this partnership between society and other players and institutions is important. So you should start looking at any partnership. But the innovation, MHRD now has innovation cells in colleges. You can have incubation cells. You can tie up with MSMEs and so on. So the opportunities abound. Just ask Google, sir. Look at DST, DBT, and every ISRO, DAE, everybody has, and write projects. So I have always done that. I've written projects. At the most, somebody will say no. So that be it. And that's okay. So you should be able to take that, but keep trying. So, and same thing for my infrastructure. I was told we will not get grants. So I said, well, it doesn't harm me. So I had 20 odd projects and I said, let them say no, but not one of my projects was turned down. And I was able to completely renovate everything, starting with toilets to state-of-the-art labs and new buildings.
Thank you, ma'am. There's another question by Bibi Mary Francis. Was it ISWAN recruitment solutions you were talking about, the database and LinkedIn?
There was an echo. Could you repeat?
Yes. Was it ISWAN recruitment solutions you were talking about, the database in LinkedIn?
Oh, ISWAN, yeah. Sorry, there's a echo on this. Yeah, so see, Gati is going to be an indigenous program. It's a pilot to begin with, but we are very hopeful. I think I'm very confident that it is going to become a national program sooner than later, because gender interventions are very, very important. Institutions have to be gender responsive. So one of the things that we lack is networking. I did not know any of you till I got this invite. But today I hope we'll be friends and we can learn from each other, and we can visit. So rather than having only international collaborations, we should have hand-holding amongst institutions, and that's happening now. NAC and UGC does it through Paramarsh and so on, and we are talking about institutions networking. And I know for me it's been a very lonely many decades of working in my lab with my own group of students, but recognition came only from international bodies because I was participating and presenting my work in conferences. There was no forum in India where I could present or my work would be appreciated, because our institutions consider only research excellence for promotion, even when you are 100% into teaching jobs. So many of those things have to change. And this kind of silos at any level doesn't help. So we don't have natural bonding or fora. So I felt that this database is best created leveraging the beautiful social media platforms, and LinkedIn is a professional platform because each of us can build our own biodata. I have seen that many times academies and all have put up performers that fill your form, and I myself am too lazy to do it or to update it. And nobody stays stagnant. You fill a form and 2 days later you may be in a different job, or you may have your best publication come at that point, or your best appointment come at that point, and so on. But you could do it at your own pace in LinkedIn. So I feel that join iSwan and we can do data mining, and we should have a directory of Indian women who are in science, be it education, be they entrepreneurs, be they in blue sky research, the frontiers, the most eminent institutions, or anywhere in a place. They're unsung. Many of the women are unsung. Give them a platform. And how much of hand-holding helps. So iSwan is what you just send me a request and join my LinkedIn, and I will add you to that, and then you can add yours. But we have to have a dialogue that remains professional, that remains just not a sob story, but a celebration of what we are able to achieve. Because I think our voices are being heard, and the young generation is aspirational, and all of us have learned how to rebound. I have not told you about the kind of maybe biases I may have experienced, but because they never bothered me for more than half a day. I just got back to my work and I was so happy doing it. But not everybody can do that, because not everybody is able to create an ecosystem where they can go back to work, and we need, therefore, to have support systems. Professional bodies are not able, so those, you'll have your own professional group, and then it's a silo. You're not helping others, and so on. So let us create through this a database and a directory and a forum for exchange of positive celebratory things. Not just to say only that, because it's case studies and other things, and knowing what is not working helps us to create what will work. So I'm not saying what we will do or will not do, but what I'm saying is approach it with, I want to be there, because that is where those women who are who celebrate their science are, and we can all gain through experiences. So join iSwan. Nirmala will be able to
Sure.
Provide.
I think through that platform only we met each other.
Yes, we met.
And I invited you. It was
I
nice.
will quickly post the thing in the chat.
Sure. I'll include all my colleagues.
Yes. Yeah. I'll leave it to you because it's collaborative. So now that's your task.
Yeah, sure. So thank you, Dr. Pratibha, ma'am. It was really informative and encouraging, and I hope everybody enjoyed the session. So thank you once again for accepting our invitation and gracing the event. So we'll be in touch, and we'll do a lot of things collaboratively together.
Yeah, thank you. So the best from education.
Yeah. Thank you, ma'am. Thank you. Bye. Who is next? I think for want of time, we can start the session. Dr. Deepa, I think you joined. I am sorry, I think the session is running a little late. So we can we get started? Yeah. Good morning. Thank you, Dr. Deepa, for accepting our invitation. So this is our team. Since we don't have time, I'm just introducing quickly. So this is my whole team from VIT. We are organizing this event, and this is Dr. Deepa from TAFR. So I request Dr. Vimala to introduce Dr. Deepa. Followed by that, Dr. Deepa, you can start your presentation. Thank you,
ma'am. It's my pleasure to introduce our next speaker for today's morning session, Dr. Deepa Kushalini, who's the professor in material chemistry at Tata Institute of Fundamental Research, Mumbai. She was awarded her PhD from University of Toronto, Canada, and she gained her postdoctoral research experience at the University of Bristol, UK. She also served as lecturer in inorganic chemistry, University of Kent at Canterbury, UK during 2001 to 2003. She is the recipient of CRSI Bronze Medal in Chemistry in 2018 and the DST Nanomission Young Career Award in Nanoscience and Technology in 2016. She is also the Fellow of Royal Society of Chemistry, President of RSC West India Section, editorial board member of scientific reports of the Nature Publishing Group, and her research areas include materials chemistry, synthesis and characterization of novel nanomaterials, exploiting inorganic structures in devices, catering to alternate sources of clean energy. Her research group also works on drug delivery devices, photocatalysis, and electrocatalysis. With this brief introduction, now may I request Dr. Deepa to take over the session.
Thank you. Thank you, Dr. Grace and Dr. Pamela, and all the organizers of this incredible event today. And to be honest with you, I'm at a bit of a loss trying to follow two excellent talks that have preceded me today. And it is quite daunting to be following, especially Pratibha Joly, and to see the incredible amount of work that she's done with respect to promoting science and promoting good practices in education. And as she kept saying, teaching people how to learn, learning to learn, which I think is an absolutely incredible sort of initiative to be undertaking. And she spent most of her life doing that. So I think it's commendable. And also, obviously, what Shobna Narasimhan presented in the first talk. I am a simple chemist. I'm a physical chemist. I'm a researcher. And I was at a loss as to what I will be talking about today. So I am going to do a little bit, with the permission of the organizers, I'm going to talk a little bit about my research. I am a scientist. I work as a scientist at my institute. So the focus is on my science, but I will also talk about my trajectory as to how I got into this position. And also, you know, my few words of sort of experiences or discussions on what I've learned in my journey so far. Towards the end of my talk, I will present, and hopefully people can, you know, relate to that. So in the interest of time, I'm going to keep the research part short. I know we're running short on time, so I'm going to help the organizers catch up on their schedule.
Yeah.
So
thank you for that.
I will try and finish early if it's okay with you.
Yeah, thank you. Thank you, Deepa. Yeah.
So I'm a chemist. I'm a materials chemist. And in this one slide, I'm trying to sort of show you what we do. We manipulate architecture of inorganic materials at a nanometer length scale. So we do synthesis. It's an experimental lab. But what we try and do is use simple fundamental chemistry, inorganic chemistry pretty much, and try and play with the architecture, morphology of material. And the result is that you can use these resulting structures in different applications. In this one slide, I'm showing you what can happen with silica, which is a simple material like glass. You can make hollow capsules here, which I'm trying to show you on the top left corner here. These are hollow capsules that can be used for drug delivery. By the same token, you can make these incredible structures. These are porous structures where you see walls of silica and there's void cavity. And these are photonic crystals. So this is quite an interesting material that allows you to manipulate the propagation of light. These are mesoporous materials and so forth. But this is silica. We no longer actually work on silica. We work on different kinds of materials, and the kinds of projects we have in our lab are that we work on photovoltaics, which are solar cells. So we work on various layers of a solar cell, and we try and optimize efficiency. We also work on batteries and supercapacitors, and these are energy storage devices. A lot of people sort of have a misunderstanding that solar cells store energy. They do not store energy. They just capture sunlight. And if you do not convert it, and they convert sunlight into electrical energy. If you don't use that electrical energy right away, you lose it. So unless you couple your solar cell to a battery, you cannot store that energy. So batteries and supercapacitors are actually much more important than solar cells currently, and trying to make good structures for that. We also work on water splitting, and this all has to do with the issues of pollution. We want to move to green, renewable sources of energy. And so we work on both photocatalyst and electrocatalyst in terms of making interesting chemicals. And we also work on drug delivery devices. So in the interest of time, what I'm going to do, I was going to talk about drug delivery devices. And as a quick thing, I will go through it really rapidly, just to highlight that, with respect to making various carriers for drugs. You see, when an organic chemist or a pharmaceutical chemist makes a molecule that can sort of eradicate a disease, the problem is, how do you introduce that molecule into your body? Because if you introduce it through orally or through an injection, the molecule experiences certain pHs and certain environments that perhaps might degrade the molecule before it can reach the site of where the illness is. So as a result, what you have to do is create little these materials that encapsulate a drug molecule and protect it, and only release the drug molecule where you want the diseased organ, wherever the diseased organ is or wherever the infection is. So people create these various structures, which are drug delivery devices. They're basically encapsulants. But the problem with these structures is that they also have to be biocompatible, or they have to have non-toxic effects on your body, because they're anchoring a molecule. The molecule obviously is good, but is this surrounding material also going to be non-toxic? And these are not easy to make, and there are lots of issues with that. So because we're inorganic chemists, we wanted to work on an inorganic drug delivery device. And one of the inorganic materials that's inherently convenient for us to work with is something called calcium phosphate, but a specific type of calcium phosphate, and that is called hydroxyapatite. As you can see, hydroxyapatite has this very fancy molecular formula, chemical formula, and making a drug delivery device that is porous, because why you want porosity, you want the drug to be able to reside inside or be anchored. And you want this hydroxyapatite to serve as a coating around the drug. And the nice thing is, because hydroxyapatite is what makes up the composition of our bone and some part of our teeth, along with dentin, then you know it's inherently compatible. But to make porous hydroxyapatite on a nanometer length scale is not easy. This is conventionally how people do it. I'm going to skip ahead very quickly and show you the kind of structures we made. What we made are these porous hydroxyapatite nanotubes. And these are very interesting. Think of them as little straws, but they're on a nanometer length scale. Because they are straw-like, it's tubular, they can uptake things through simple capillary action. Here's some TM images, and I hope you can see the hollow cavity on the inside. So what we did is that we said, can we use these as an easy way to deliver drugs? And it turns out, so first of all, we spent a lot of time characterizing it. I will skip this part to ensure that it was the right phase of calcium phosphate, that in fact, it was hydroxyapatite, okay? Suffice it to say, it is hydroxyapatite. And the other thing I want to highlight, it has a huge surface area. The internal cavity of the straw has huge volume associated with it compared to a dense phase of hydroxyapatite. As you can see, this number is much smaller. This number is substantially bigger. And what can we do with this? Well, we can do something very interesting. First of all, it's biocompatible. These are assays. As you can see, the yellow histograms all fall around the same point on the y-axis. And on the x-axis is the concentration of my hydroxyapatite nanotubes. So means that when I increase the concentration of these tubes in a Petri dish containing lots of cells, these are fibroblast cells, they do not die. They are all alive, that there is non-toxic effect, obviously. But in addition to that, we can encapsulate simple molecules. Here's a simple example of rhodamine. Rhodamine does not go inside fibroblast cells. This is a confocal microscope image showing you that there is no rhodamine inside the fibroblast cells, because if I introduce rhodamine by itself, the cells do not uptake it. What the experiment was that we introduced rhodamine, we let it incubate, and then we washed away the excess rhodamine. In a period of about 4 to 6 hours, no rhodamine went inside the cells. However, if I took my nanotubes and through capillary action, I put rhodamine inside my nanotubes, and now I introduce them to the cell, what happens? The cell uptakes the rhodamine. So now you have a molecule that normally does not bypass the cell membrane, can now enter inside the cell because it's coated. There's a hydroxyapatite nanotube. Now the nanotube, it turns out, is very conducive to the cell membrane, and the cell membrane uptakes it. So I've not had to change the structure of my rhodamine. So think of rhodamine as a drug molecule that you can therefore introduce easily and let it get inside the cell. And as a result, we've looked at various molecules, and these are all images of the nanotubes. As you can see, they reside inside the cells. I won't spend too much time. I will just go through one quick study we did with respect to a cancer drug called paclitaxel and doxorubicin. So in paclitaxel, what we found is that, and I'll just go right to the last slide of the research, just so you want the experiment that I'm trying to show you here is we did a control experiment where, in addition to the nanotubes, the data in the red is shown of the nanotubes, and the data in blue is of a dense hydroxyapatite sphere. And what we did is we coated these material with paclitaxel. So the nanospheres are coated with paclitaxel. The nanotubes have paclitaxel inside it. Both are made of hydroxyapatite. Question is, which one is better at eradicating cancer? In this case, this is a cancer cell line. Okay, and what you want to do is you want to destroy the cell line. So what you want is these histograms to go down as a function of concentration. And what I want you to realize is that the red histograms are going down faster than the blue histograms, suggesting, because the data has been normalized to the number of cells and the amount of drug, that for the same amount of drug that you introduce in your nanotubes, it more efficiently is able to destroy the cancer cells, as opposed to if you introduce the drug as if it was a coating on a dense nanoparticle of hydroxyapatite. So the carrier, the type of drug delivery device, also not only introduces the drug at the site of disease, but it does so in a more efficient way. You use less drug and destroy more of the diseased molecule. Okay, so at this point, so as you can see, this was it was like a crash course of about 3 years worth of work that I presented just to show you how we can play with the architecture of these nano inorganic materials and make some interesting materials out of it. Now, at this stage, what I'm going to do is, because of the way this workshop or this seminars are unfolding and the last two lectures went, I thought maybe it might be more beneficial if I discuss my personal experience as to how I ended up where I am currently. As in case you do not know where I am, I'm at an institute called TIFR. It's in Mumbai in India on the West Coast. Now, I should start off by telling you a little bit about my background. So just to tell you, I was born in India. I was born in Delhi, but when I was very young, when I was about 9 years of age, my parents emigrated to a small island in the Caribbean called Trinidad. So I did my primary high school up to the age of 9 in Delhi. But after that, we moved to Trinidad. And from the age of 9 till the age of 16, which was most of my high school, I did in the Caribbean, in Trinidad. And that was very interesting. And we can discuss all the experiences I had as a girl. living with, we were a small Indian family and we did not have any other Indians around us. And we were in this very predominantly African setup in the Caribbean. And it was very interesting. And so I did most of my schooling, high schooling there. From that point onwards, my parents again emigrated and we moved to a place called Vancouver in Canada. And at that point, I then started going to university and I did my Bachelor of Science in Chemistry. And I should point out to you, it's very interesting at this stage, I should say, because in the Caribbean and Trinidad, I did something called O-levels. O-levels is equivalent to the board exams in India. And I stand before you as a PhD in chemistry, but during those exams, I should tell you my lowest mark, I did board exams in all the sciences and maths and so forth. And my lowest exam was in chemistry. I scored higher in biology and physics and English, and French and other funny subjects, but chemistry was my lowest mark. But when we moved to Vancouver, I entered university, and in your first year, you're allowed to do as many topics as you want. And it's only you pick your specialization in your second year. And again, I picked my specialization as a chemistry, I think, as a more of a challenge more than anything, because it did not come easily to me. I should highlight to you. I come from a very simple family also, I should point out. My parents are not scientists. My father is an engineer. My mother is a housewife. I do not come from a family of scientists. I am a Sindhi. And in fact, business is more prevalent in my family, or being part of a business family, you know, sort of joining a business, as it were, and being an entrepreneur is more applauded as opposed to going into education stream. But for whatever reason, I somehow persevered and I did my honors in chemistry in Vancouver. After finishing that, what I ended up doing was I ended up doing a PhD, and I did not do the PhD in Vancouver, but I did the PhD in a place in Toronto, which is on the east side of Canada. I left my family behind. My parents continued to live in Vancouver, but I moved to Toronto and I did my PhD there. And I should, at this point, highlight the reason for doing a PhD was not because I was so absolutely enthralled with science or research. It was more out of shared desire to be independent. It was a shared desire to basically try and move out of my family's home and try and figure out what it is I want to be and what I want to do with my life. You see, when you do a PhD in science, there's something small that people sort of don't highlight here, but for me, it was a big deal when I was about 19 years of age, which is you get paid to do a PhD. You get funding. So you do not have to be dependent on your parents financially. And that was a big deal for me. So it allowed me to say that I could earn money, still be, you know, in university and learning something, being some form, getting an educational degree, but I could be financially independent. And that is the reason that I was able to move to Toronto, because their life is very expensive and you need lots of money to live. And, you know, you don't get things like hostel, you have to find your own apartment to live. And during my PhD, I also worked part-time to earn more money so I could sort of, you know, be financially independent completely. After finishing my PhD, I didn't want to get a job easily. So I moved to England, and there's a place called Bristol, and I did my postdoc there. Again, the idea was more out of desire to travel to Europe as opposed to wanting to do a postdoc. But suffice it to say, it allowed me to, you know, it's like a job, you get money, they fund for your visa. And I found a lab that I was very excited to work with. I found a supervisor that I felt that I could talk with, you know, that I could be friends with. And so it was a very good experience there. And then in England itself, after finishing my postdoc, I actually got a faculty position as an assistant professor in a university there called University of Kent. And I should tell you, all this time I'm alone. I'm single, I'm not married, but I'm just trying to find my own way in life, as it were. So in England, I stayed for a few years. But at some point, I decided that I wanted to return to India. And this was in around 2004. I came back to India and I joined PIFR. My parents still live in Canada. My family still lives in Vancouver. They have never returned back to India, but I did. So I've had this sort of very interesting circular trajectory, which most people don't normally follow in India, which is once you leave India, you stay outside. But now I've been back and it's been, almost 15, 16 years. And I'm settled. And I got married much later in life. I did not get married young. And I got married when I returned to India. And that has been my trajectory, basically. And like I said, the desire has just been out of sheer, one aspect is to be independent. One aspect is to pursue what I want to pursue, as opposed to being dictated by what others want me to do. And it's not always been easy, but it's the thing that I have sort of followed, or the policies that I followed in my life. At this point, I want to highlight a few things that I've learned along the way that I think maybe the younger generation, this is more for the students in the audience, that I would like to sort of bring about. I mean, we've had excellent talks, and I just wanted to sort of highlight a few things that maybe are not at the forefront of many, at the forefront of their thought process, the students' thought process. And in that respect, I want to highlight that, when you think about what it is you want to do in life, you inevitably think about things like, the kind of knowledge you're gaining, the kind of degree you're getting. And these are called hard skills. Along the way, you want to be proficient, and you want to have, things like how to use computers, computer programming, data mining. You want to speak a foreign language and so forth. These are all hard skills, and they're very important if you want to be successful in life, which I hope everybody does. And, but success is measured in different ways by different people. But these are called hard skills, and this is something we learn along the way. And I want to, again, remind you that when it comes as a hard skill of chemistry knowledge, I was not the brightest chemistry student in my class. I was not at the top of my class when it came to chemistry. But it's because part of it is that it was a challenge that I pursued it, and I'm standing here before you as a chemist. So it's not about what you like to do or what that you are instinctive. It shouldn't be what you're instinctively good at. It's more about what you like to do. And so these are the kind of skills we learn in life. We learn, especially when we're young at school, we take various courses, and these are important, and it's important to be proficient in them. But having said that, I think life is equally needing, to be successful in life, you equally need a large amount of what I call soft skills. And I want to sort of highlight a few soft skills that are generically needed, but also some soft skills that I think women need to have. Okay, at least this is from my experience, and maybe it might ring a bell or two with the audience members. So when it comes to soft skills, these are the words that people use. What is your work ethic, which is how responsible or disciplined you are. This is not something you're taught, and this is not something that you can be taught. Either you have it instinctively or you personally develop it over time. No one can force you to do these things. There's something called interpersonal skills, which is, how friendly you are, how empathetic you are towards other people, how good you are at networking. Some people have it, some people don't. I'll be the first one to say I'm not a very good networker. I tend to want to be alone most of the time. But anyway, if you are good at networking, you will have a good set of, just like what Pratibha was talking about, a good set of interactions where perhaps that can be sort of a support system for you. Time management. Think of it from your schoolwork. Are you the kind of person who hands their school assignment and homework on time, or are you always asking for an extension? Because if you have those tendencies when you're young, you're going to have those tendencies later in life. And trust me, when it comes to a job, when it comes to a profession, time management is very important. Your boss may not be as lenient as your school teacher with respect to your assignments being given on time or not. Leadership, attention to detail. And then there are these other soft skills: communication, teamwork, adaptability, problem solving. These are all buzzwords. You can reflect on them on your own time, and you will see whether you are good at these things or you're not. But I want to highlight something very interesting. Out of all of these soft skills, teamwork, friendliness, networking, problem solving, communication. I want to highlight, in fact, there's one skill, one soft skill, which which is perhaps the most important soft skill to have currently in our life. It will help you more than anything. And I'm not sure how many of you have realized what it is. I'll bring up these words again, and you can sort of try and think about which soft skill is the most important. And I'll show you something from LinkedIn. Pratibha was mentioning LinkedIn being a fantastic website. And if you see, what comes at the top is communication. You know, what comes at the bottom is a friendly personality. It's irrelevant in life whether you're a friendly person or not, but you will be more successful in life if you know how to communicate. And I cannot, and for me personally, I cannot stress this enough. What do we mean by communication? We mean by communication things that you speak orally, things that you write down in a report, the ability to send an email, the ability to talk about your ideas effectively. You know, if you looked at the two talks, if you sat through the talks of Shobana and Pratibha, I guarantee you the reason you were so impressed by their talks was because of their communicating ability. They were able to impart their ideas in such a clear way and using language that you could understand, and in a manner showing you the right kind of data in the right way that made a sort of impact on you. And that is about communication. Okay, they may not be the best physicists in the world. They may not be the best teachers in the world. They may not be the best women scientists in the world. Okay, but because of what they talked about during their presentations, you were so impressed with, you have a greater respect for them. You are so impressed with them that you will look out for them the next time you see them because they made an impact on you. All right, and this also happens daily in your work. It's about how a teacher talks to a student or how a student talks to a teacher. If you're able to talk in a manner that lets the other person understand you clearly, it's perhaps one of the most important skills to have. And it doesn't matter the language you're using. You can use Hindi or your native dialect, but you'll be surprised how ineffective we are at talking and communicating our ideas in a way that the audience understands. And I think that is one skill that I would like all of you to please keep in mind. Think of it from the way you write an email to somebody. You'll be surprised, you know, I work at DIFR and I get lots of students who want to come and work with me. They want to come and do their PhDs or projects with me. I get even faculty from various universities contacting me. And you know what? I'll tell you about communication. You'd be surprised also how many emails are written, dear sir, I read your paper. I was very impressed, blah, blah, blah. I said, you know what? You've not done a simple homework of communicating that you actually know me, that you've actually done your research about wanting to find out by just writing the word dear sir. So communication means taking effort, understanding your audience. What is it you want to impart to them? And same thing when the student talks to a teacher, you want to make the best impression. And the teacher talking to a student, you want to make the best impression. So please keep that in mind. Having said all that, these are just natural soft skills that people need to have. But I want to now talk a little bit about the soft skills that I think women need to have. And I feel that I need to spell this out perhaps at this particular seminar. And these are just my lessons that I've learned in life. So forgive me if you find that they're incorrect, but these are just personal experiences. I think one of the most important things you need to have in life is ambition. I think personal drive, personal desire to do something is the most important thing, and not waiting for someone else to propel you further. Not waiting for your father, for your mother, for your husband, for your brother, for your teacher, for your mentor to propel you, to tell you what to do next. But for you to have personal ambition that, you know what, I want to do something more than what I see in front of me. If you cannot imagine that for yourself, there's no way that other people are imagining it for you. Whatever other people are imagining for your success is always going to be less than what you want out of your own life. And I think it's very important for you to benchmark goals. Like I said, for me, my ambition was to be independent. Okay, it was not to be a professor. It was not to be the richest person. It was not to be the most famous person. It was to be independent and financially completely independent and be successful, be comfortable, be proud of whatever I ended up doing. And that is why I pursued the trajectory that I did. And I think that is very important. My parents did not want me to do a PhD in science. So it's not always about having a support system around you that takes you. People who, how you measure success is different for different people. I feel that I am as successful as I can be based on my environment, based on my ability. And I'm very proud of what I've achieved. It is definitely far more than what my parents anticipated, or far more than what my family anticipated, but it's also different from what they wanted. But it's what I wanted, and that is the reason I'm here. And so, this is sort of my thing, which is that other people will want different things. You have to decide what it is you want, and you need to be focused on that. You cannot let other people easily sway you from your own life. You get one life to live. This is not a dress rehearsal. This is not something that, oh, I will get a second chance. I will do it later. I will do what I want later. Right now, let me please other people. I think it has to be a balance, but you have to realize that you have to live within yourself. No one else is going to live your life for you. And therefore, you need to be focused on that. It may not happen in day one. It may not happen. But, look at Pratibha. She's a perfect example that she stayed focused to her dream. Even now, even after retirement, she's not giving up. It's kind of like self-perpetuating. Once aadat ban jati hai, once you have that habit that you are going to drive your desires further, no one can stop you. Okay? And this, again, I want to reiterate, has nothing to do with academic capability. It doesn't mean that you need an A+ in that subject to pursue it. The third thing that I want, and this is especially for Indian women, is I want you to consider actively developing a skill of confidence as opposed to arrogance. There is a fine line between the two. Humility is not the opposite of confidence. Humility is the opposite of arrogance. Being humble is, you have to realize, being humble doesn't mean putting yourself at the second, in position 2, as it were. There's nothing wrong with propelling yourself to be in position 1. And that's about confidence. And like I keep saying, confidence doesn't come just because you get an A+ in your exam. Confidence is about belief in yourself. If you don't believe in yourself and your capability and that you can reach from here to wherever it is you want to go, no one else is going to believe it for you. No one else is going to give you confidence. You can have a good support system. There are lots of these initiatives that Pratibha and Shobna are mentioning, which I think are fantastic, because we do need confidence at times where we lose it, and we need a good support setup around us. But even that is not going to be available to you 24 hours a day, every day. So part of it is learning to teach yourself how to believe that what you are doing is correct. You have to have faith in your ability. You have to have faith in that the direction you're pursuing is honest, is ethical, and that you are not harming anyone along the way. So why should you, feel guilty for pursuing your dreams? Next one is perseverance. I've written. Perseverance comes because we all fail. Failure is part of life, regardless of the path you take, regardless of whether you follow what your father is telling you or what your husband is telling you, or you follow your own dream. both paths will have failure in them. I can guarantee you this. There will be success, but they will be failures. And the thing from failures, everyone says is, oh, you should learn from your failure. I agree, you should learn from your failure. But what I feel is even more important is to forgive yourself when you fail, is to realize that it's okay to have made that mistake. It's not the end of the world. You put yourself out there, you made a mistake, you wrote a grant, you didn't get it accepted, big deal. Tomorrow you will write another grant. Tomorrow you will write the exam in a different way. You will learn more. You will retake the course if you fail the course. Do not feel completely lost when things do not go according to plan, because all through your life, at least for my life, things have not gone according to plan. But you have to persevere. Along the way, you have to at times be selfish, and along the times you have to be selfless. There's nothing wrong with being selfish at times. We are all human beings. We all deserve to be on this planet. We all deserve to have a life that makes us happy. And if at times you have to be selfish for it, so be it. And that is about a balance. And at times you have to, yes, relent and give yourself to others. But you have to decide what that balance is. No one else is going to. And if you decide to give your time to someone else and give other people priority, then it's important not to be angry at them for that. This was your decision. This was your decision to follow that path, that you are going to sacrifice your XYZ to do something else for someone else. Because you weighed the pros and cons of being selfish versus selfless. You made an active decision. And at that point, if you've made that active decision, then you have to take ownership of that decision. And then say, okay, I'm going to make the best of it. I am not going to be miserable because of the direction I've taken. I have taken this, I will try and find happiness. And if I cannot find happiness, then I need to change the direction I'm following. And I have to live with the consequences. Okay? And the last one is about independence, interdependence, and dependence completely. And what I've written there is, how easily do you relinquish control? And what do I mean by that? How easily do you relinquish control of your life? How easily are you persuaded by other people's opinion as to what you should do? Because, you know, there are lots of people in this world giving gyan, giving advice. Oh, you should do this. Oh, you should do that. You should wear this. You should speak like this. You should sit like this. You should eat this. Question is, when do you decide how much you will follow in their footsteps and how you will do on your own, and to live with that? And there's nothing wrong, absolutely nothing wrong with being dependent on other people, but there's also nothing wrong with wanting independence at times. So finding a balance for yourself and being active in that decision, not being a passive person who just follows the crowd and says, well, they had a good life following that route. I will be dependent on that decision and I will follow their route. Do not do that. Be an active participant in your life, please. Make active decisions for yourself. And when you make those decisions decisions after a great deal of thought, intelligence, and then take ownership of those decisions, of those paths you end up taking. Okay. So these are sort of the words that I wanted to sort of highlight, that I have, you know, depended on my entire life to keep reminding me why it is I'm doing what I'm doing. And finally, for the students, I want to highlight a few things about the advantages of being a scientist. You can do anything you want. Pursuing science does not mean that you will be a scientist in life. In fact, I will tell you, if you pursue science, it's perhaps one of the main areas of education that will open more doors for you as opposed to closing doors for you. And what do I mean by that? I will highlight the last point here. India is in a great there's a great dearth of something called patent lawyers. What are patent lawyers? Patent lawyers are lawyers who patent scientific, in many cases, scientific discoveries. So these lawyers need to know scientific language. They need to understand scientific principles so that when a scientist, let's say from ISRO or from some DBT institution or a CSIR institution comes and says, I want to patent this discovery, the lawyer must be able to understand the scientific concepts behind it. So as a result, you know what patent lawyers are? Patent lawyers are people with either a MSc or a PhD in science. Then a law firm hires them and gives them a law degree for free, because it's a lot easier to teach law to a scientist than it is to teach science to a lawyer. All right. Lawyers cannot subsequently get an MSc later on in life. Okay. But an MSc person or a PhD person can get a law degree. And in fact, patent lawyers are one of the most wealthiest branches of law where you earn a lot of money. You can have MBAs. There are universities, at least in America and Europe, I know, if you have a PhD in science, your MBA degree becomes 1 year long. It's no longer a 2-year or a 3-year MBA. So it's a shortened MBA, and it'll allow you to enter management positions at pharmaceutical companies and things like that. Okay. Working on Wall Street is very interesting, or working on the, you know, because when you learn science, you learn statistics, you learn how to analyze trends. So in fact, when you learn the concepts that you learn in science actually are applicable to many diverse fields. And there are lots of new, and I shouldn't say new, but lots of areas, lots of professions that will be very willing to hire people with scientific degrees, because they know you've learned how to do problem solving. You've learned how to do trend analysis, statistical analysis. You know data mining if you've done those sort of things. You know how to work with computers. You're very literate in problem solving. Okay. And by the way, even if you pursue science and become a scientist, you can be relatively wealthy. You can invent things, patent them, and get rich and so forth. All right. Plus, if you get a PhD, you can travel the world. I should point out, if you get just a law degree from India or an MBBS degree from India, you know, you cannot practice law abroad, or you cannot practice medicine abroad, because you need additional qualification to do that. However, if you get a PhD in India, you can become a scientist anywhere in the world. It is completely translatable to the entire planet as well. You can go and travel. And in fact, as a scientist, as Shobna pointed out, you know, we get to travel a lot, lots of conferences, lots of interactions, lots of funding, and it's really a great life as a scientist. Plus, you know, one thing I've not highlighted here, you don't have a boss. I do not have a senior boss that I have to report to every day. So it's sort of a Peter Pan kind of existence, which is I get to learn and be a child every day and learn new things with my students. Okay. So I'm not sure how we're doing on time, but I will end here. And this is my small research group, funding and so forth. And I will be happy to take any questions, but I'm not sure if there will be any questions from my side. Anyway, thank you very much. And again, thank you to the organizers.
Thank you, Professor Deepa, for sharing your experiences during your academic journey and the technical information as well. I have a question from Dr. Kavita Tirumurugan, faculty from VIT. One major quality of you that propelled you all along the various trajectories.
One quality is no one quality. It's perseverance and just saying that I will do what I want to do. It's about being, you know, and making sure that I don't hurt people along the way. You know, as long as I was not hurting people along the way. I'll tell you the conversation I had with my parents. I remember my mother, for those of you who maybe here your parents wanted all of you to do PhD. Like I said, my parents were not very keen. They wanted me to be a school teacher, you know, after I finished my BSc, or they wanted me to be a doctor in medicine. And because being in medicine, you have to pay a lot of tuition fees. I could not afford it. And I didn't want to depend on my parents for that. And I didn't think a school teacher education teaching was something that I was feeling very attracted towards. So when I said I want to do a PhD because I want to think about life later on, you know, in the meantime, PhD will give me some time to realize what I want to be in life. I convinced them simply by saying, you don't have to pay a penny. I will, you know, fund it myself, the tuition fees, the stay, the food, everything, hostel, apartment, everything I'll do myself. And I found the supervisor. I got into a good university, a good program. So, and then my mother said, well, why do you want to do a PhD? It's not like you want to win a Nobel Prize. And I looked at her and I said, well, why not? Why can I not win a Nobel Prize? And then this is where, you know, it's sort of a light bulb went into her head, or went on in her head. And I realized that, you know what it is? We ourselves sell ourselves short at times, which is, I can't do that. I can't do that. I've not won a Nobel Prize, but that doesn't make me unhappy in the sense that like I said, what I like about my job is that I come when I want, I leave when I want. I'm working on something that I'm very passionate about. It's like a hobby. It's not a job 9 to 5 that I wait for 5 p.m. or 7 p.m. to happen so I can rush home. I'm thinking about my work all the time. It gives me flexibility. And, you know, I now have a mother-in-law who, you know, my husband is not in science, he's in finance. And she actually tells him, you know, that he married somebody who is much better at charting her life, because I can come home and take care of her randomly. You know, he's stuck in a 9 to 5 job kind of thing, right? So, and she literally says, who would have thought that, you know, being an eternal student will allow you this kind of a life? And I get to travel, you know, and so, and it's a question of, like I said, what your priorities are. Life will always give you hurdles, but you kind of have to stay true to yourself more than anybody else, because only you can put a smile on your face. No one else can put a smile. If internally, mentally, you're happy, all the shit going on around you, you will still be smiling. Think of it like that. That is
Thank you.
Okay.
Hi, Dr. Deepa. It was in fact a very enlightening talk, and thank you for so many tips that you shared with us. I just have a very quick question. Of course, being in research, we all know the importance of networking, but what would you tell for people who are introverts, like who would find it very difficult to network or to you know, establish connections with people, and who are just stuck with within their comfort zone? So,
I'm not sure if I'm the right person to see. This is easy for me. I am talking to people, all females here. This is a very comfortable environment to be talking in. Okay, there's no threat here. I don't have any, you know, sort of people rolling their eyes. I can't see anybody. I can only see the 6 of you, right? So it's a very non-threatening environment. So this is an easy kind of networking. The networking I don't like to do, and I've never been very comfortable at, is, let's say you go to a conference and there are people, and, you know, men instinctively, I'll tell you, when I came for my job interview in TIFR, okay, I had applied, I had written, they gave me a schedule, come give your talk, you will meet with faculty. Despite all of that paperwork, there were 2 or 3 faculty in the institute who thought I had come as an interview for a postdoc position, not a faculty position. So they didn't give me, you know, when the allocated schedule of meeting them was there, they did not, you know, this assumption over, because I look short and, you know, I'm 50, but I don't look 50. You know, when I was 30, I even looked younger than that, right? So there was this impression of choti ladki aayi hai, koi, you know, student wouldn't. So, and as a result, even in a public environment, I don't get that confidence that people will be willing to talk to me. So I am not, but you have to, it takes effort. It's kind of like you have to develop a habit. And there are many, you know, it's kind of like brushing your teeth. You're not born knowing you have to brush your teeth every day. It's a habit you develop every day when you're young, right? So just like that, it's sort of a habit, which is you have to force yourself out of your comfort zone and say, okay, I will force myself into an environment where I may not be respected or I may not be looked at favorably, but I will put myself in that position so that I can start talking and making an impression. It might take them 5-10 minutes later, but then they will give me respect. Okay, women, at least this has been my experience. I don't instinctively get respect. You know, when 60-year-old bearded man walks into a room, they will instinctively get respect, whether they have a PhD or not, just by looking at them, right? Whereas when I walk into a room, people look, they're not going to instinct. So you have to realize this is the society we live in. And, to change society, this, maybe some of you will feel this incorrectly, but I do not think governments and large initiatives and doing morcha in the public and asking for handouts are the way to gain respect. If we want equality, we have to give equality, right? You have to open the door for your husband if you want also your door to be opened by him, right? You also have to pay for dinner sometimes when you're in a restaurant if you want him to pay for the dinner for you. That is equality, because that is not lifting any big burden. It's a mental thought process. So same thing, if you want equality, it's about changing society around us. And for me, society is made up of you and me. Women make 50% of the society as well, right? So it's about how we treat each other. And if we are in the habit of wanting concessions, okay, sometimes it's needed. I'm sorry. Yes, if you are in the village and you don't have access to toilet facilities, you need government to step in. If you are doing child marriages and all of that, you need the government to step in. But if you live in a metropolitan city in India and you're earning a salary, okay, you have every right to participate in the equal life. Okay. You understand what I'm
saying? Thank you so much.
So that is, I've said many things, but it's about a thought process.
Thank you.
There are a number of questions. Yeah, Nirmala, can I? Yeah, hi Deepa. It was very, very interesting, and I think many people would have enjoyed at least listening to this talk because it would have really motivated them. I think the main issue with India, and since you have been outside India and come back, you are able to have the freedom of independence thinking. The major problem in India, people live for others. They think what others will think and what might happen if I do out of way. So I think people should come out of that mindset to be independent. So what is your view on that?
You see, I don't think by being abroad, I was abroad, yes, for 25 years or something like that.
That makes a difference.
Yeah. I don't think being responsible for others is a mindset that is exclusively located for India. My parents have two daughters, my sister and me, and that's it. They live alone. We do not have an extended family. They're 80 plus years old now. They live alone. I live in India. I have to live with that decision. Okay. You have to live with your consequences. So you have to decide, and now my mother says, I'm happier because she's happier that every day she talks to me and I'm laughing and telling her various things and she's very proud of what I've done. But maybe 30 years ago, she would not have been. She was worried. She was very worried that I was going off on my own. My parents lived a very insular life. You see, just because we went abroad doesn't mean my parents and my family had a very liberated view. In fact, we became more insular. They protected us far too much. Okay, and that is why I was so desperate to be, on my own. And so the thing is, you have to realize, how can you to make my parents happy? I had to pursue my own happiness in the process. And now I can give it. I have, as a result, I visit them very often and every year, and we do lots of things. And it's a much better relationship we have now, simply because, yes, at some points I was selfish. I explained it to them. We did not fight about it. But what I'm trying to say is everybody has to find a balancing act. All right. There's no one solution. And the title of my talk, I didn't highlight it. I said of trials and tribulations of unconventional life. There is no conventional life. All of you have unconventional lives. Okay. All of you have different problems. There are no two people who have the same things. But the focus should be on, can I live with my decision? And please realize the decision is with you. As much as we like to think, oh, it's my mother-in-law who's making me do this, or my husband is making me do this. At the end of the day, you are allowing yourself to follow that path. And if you are doing it, please take ownership of that. It is your right not to take that path also. But you, just like I have to live with my consequences, other people have, you also have to live with the consequences. If you sacrifice your happiness for something else, then do it with a happy face. You see, you can't have it both ways. You can't say, I will sacrifice myself for you, but then I will live miserably and I will make you pay and regret and, you know, be upset at you for the rest of my life. That is a pointless life to be living. We only get one life. So please, that is my request, because I see so much unhappiness sometimes and I say, well, why are you doing it? What is the point of that sacrifice if you're not going to make your child, if you think you have children, you sacrifice, your children know you're unhappy. Okay? It's not easy. I'm not saying, no one said this was going to be easy. None of us, what we're doing is easy. Learning and education, PhD in physics, understanding thermodynamics is not, it's hard work. But life is hard work. But you have to do it with honesty and you have to do it with a thought process that says, look, I have an ultimate goal I want to be at. And if I'm taking this path, I am taking this path. Then be happy on that path, please.
Yeah, excellent. I think that mindset will slowly evolve. It's evolving and it will evolve more.
It's not, it's like I said.
No, just love what you do. That I think that makes a difference. Whatever you do.
Only you can make yourself happy. Please keep that in mind. And if you put a smile on your face every morning, everybody around you will be thankful.
Thank you, Deep.
Thank you.
Nimla, your voice is very low.
Am I audible now?
Yeah, yeah.
Yes. Yeah. That was a very interesting talk, Deepa, and I really enjoyed each and every line of yours. And I totally, believe your words. I think happiness is, we have to invest self. It was really interesting, and we'll catch up later. We'll discuss more on this. Thank you so much. Thanks once again for accepting our invitation. Thank you. Have a nice day. Bye. So with this, we'll move on to the next session by Dr. Vatsala Thirumalai. Oh, Dr. Vatsala has joined. I'm sorry, Dr. Vatsala, I think we are running late of time. So we can, without much introduction, this is a group, team of members organizing the event. So we'll get started with your presentation with a short introduction of yours by Dr. Vimala. Dr. Shak Mangai.
Hello, ma'am. This is Mangatkar CR from CNR. Can you hear me?
Yes, I can hear you.
Yes, okay. Okay, I want to give a short bio about you. So, Dr. Vatsala Thirumalai is working as an associate professor and senior fellow at National Center for Biological Sciences, Bangalore. Dr. Vatsala Thirumalai's research interests are in development and assembly of motor circuits, neuromodulation, and the dynamics of intrinsic and synaptic conductances. Madam was awarded a PhD in neuroscience from Brandeis University, Waltham, US, and served as postdoctoral fellow at Cold Spring Harbor Laboratory, New York. She uses the larval zebrafish as the model system to study different questions at multiple scales, from molecules to behavior. The embryonic and larval stages of these fishes are transparent, which enables the researchers to directly observe the developing internal organs, including the brain. Dr. Vatsala received the prestigious Shantishwara Bhatnagar Award in 2020 for research on neural networks that control movement during development and adulthood in animals. With all these few words of introduction, now I request Dr. Vastala Thirumalai to deliver a talk on fishing expeditions in the brain. Thank you.
Thank you, Mangair Karasi, and also thank you, Dr. Nirmala, and all the other organizers. It's indeed an honor and privilege to be part of this meeting. I mean, I have a very, very tough act to follow. Dr. Deepa has basically said everything that there is to be said on this topic. What I can do is perhaps just offer my scientific journey. Sorry, I think there was a power cut here. One second, let me get the presentation up again. Can you hear me now? Okay. Are you able to see my screen?
Yeah. Yes, ma'am.
Okay. Okay. So I am from the National Center for Biological Sciences in Bangalore. And first I'll begin with talking about my scientific journey and perhaps tell you where it mattered for me, the different decision points in my life that actually led to where I am today. So basically, I was born in Chennai, where I grew up and attended college. So we were actually in a suburb of Chennai called Krompet, which is near Tambram. For those of you that know Chennai very well, I am the last child among four. My parents have one son and three daughters. I'm the third daughter. My parents actually did not go to college. They worked for the state government of Tamil Nadu. So we were a very much middle class, lower middle class family. But one thing that made a huge difference for me and for my siblings was that my parents placed huge value on education. They basically said that, you know, we will support you for you to study how much ever and whatever you want to study. And this is what, you know, was a huge encouragement for me early on in my life and also for my siblings. So why I'm saying this is that, you know, as a parent, I'm sure there are many parents here in this forum. It's important for you to tell your children that, you know, you have their back, you know, you'll support them in their dreams, because after all, what are we born for? We are born to realize our dreams. And if parents don't support the dreams of their children, who will, right? So after finishing school, I finished BTech in biotechnology from Anna University, also in Chennai. We were the very first batch of students in this particular program. And it was very, very good. It was a very revolutionary program that they had, combining maths, physics, chemistry, and biology, first of its kind in the country. And it was very, very useful. You know, I did not know until I entered PhD in neuroscience how much of a role maths and physics played in biology, in understanding the nervous system. I will clarify this a little bit later in my talk. There are many fundamental principles in physics, fundamental principles in mathematics that are important, needed for understanding biology. So if you are a student and if you want to do biological sciences research, it's very important that you build a very broad base. You have to take your math and physics seriously, because science these days is interdisciplinary. You can make a difference if you work at the confluence points of different disciplines, because you'll be able to borrow ideas from two disparate disciplines and bring them in to enlighten aspects, be it in biology or be it in chemistry or physics or mathematics. You know, when you marry the principles from two different varied disciplines, that is when you can make a breakthrough. So it's important to appreciate interdisciplinary training. Okay. So after finishing BTech in biotechnology from Anna University, I went to do a PhD in neuroscience. And this was because I had already made up my mind by the time I was in 12th grade that I wanted to be a scientist and that I wanted to study neurobiology. Somehow neurobiology appealed to me in those days, and it still does, as something that is very complicated, bordering on philosophy. And therefore, you know, I thought that it was instinctively attractive to me. And you know, after finishing the bachelor's, I was ready to take up a full-on PhD program in neuroscience in the US. I went to Brandeis University, right? So through all this process, it was my inner search for meaning in my life that drove me to these paths. And once you're in a PhD program, you know, after that, the next steps become subsequently relatively easier for you to take. What is the next step? What is the next step? The big step is deciding what is the career that you want to be in. And so after that, you know, once I finished PhD, I knew I wanted to have my own lab someday. And therefore, I did additional postdoctoral training in the labs of established labs, and came back to India in 2010, in November of 2010, where I've been at NCBS since then. And now I have a group that studies locomotion in using zebrafish as a model organism. So as I told you earlier, my passion is neuroscience, and the motivation for having this passion is a deep down yearning for understanding how things work. And to me, you know, the brain is probably the most complicated thing out there to understand. And that is why I want to be in neuroscience, and I want to understand how is it that the brain works, and how is it that it develops, and this complicated organ wires up by itself and somehow functions. How does that happen? And these are the big questions that I tackle in my lab to this day. So in terms of focus areas, I look at control of movement. How do organisms move from one place to another? Because in my mind, you know, cognition and thought and emotion are very, very complex, advanced concepts. Movement is something much more basic. Movement is something fundamental to survival, because if an organism cannot move, then it cannot survive by escaping predators, or it cannot survive by being unable to find food. So that's why I choose to study something as basic as movement. And my idea is that if you understand movement completely, that is the template upon which you can build up and understand much more complicated cognitive tasks, such as communication, you know, languages, or you know, emotion, all of those things. And along the way, to tackle these questions, I acquired expertise in electrophysiology, which is the ability to record electrical activity from the nervous system. I spoke about it in the previous slide. So this is an example of interdisciplinarity, because the nervous system uses electricity to function. Electricity is the means by which one neuron communicates with the other. Therefore, you have to have a basic understanding of the physics of electricity, and using that basic understanding of the physics of electricity, you can make technologies and tools for either looking at what is the electrical signal going between the nerve cells and how you can manipulate it, how you can change it, so that you can then ask, what happens if I, you know, manipulate the activity, what happens to the behavior? And that's something that we do in my lab to this day. Also, as part of this mission, what we do is that we look at behavioral analysis, which is, how does the fish swim? How does it move from one place to another? What kind of tail beats does it do? What kind of fin movement does it do? All of those things in a very, very detailed manner, this focus on detail and get the quantitative aspects of the behavior. Then, of course, microscopy. Genome editing is such a hot topic. I'm not sure, but maybe many of you know about genome editing tools, including the CRISPR-Cas9 toolbox, which got the Nobel Prize last year. And also a whole bunch of computational neuroscience using mathematical methods to understand, to build models of the brain, and then to understand it at a much more deeper and more detailed level. So this is what we do in my lab today, and this is what I had worked for over the last 20 years or so to build slowly by slowly, brick by brick by brick, and this is where we've arrived. Right. So I want to throw this slide before I go into my science part of the talk. So I told you that, the nervous system works with electricity, and therefore I'll show you pictures like this, where we are recording the electrical activity of nerve cells, neurons in the brain. So this is one such neuron in the top. And you see these nice little wave-like signals, right? And then sharp spike-like things on top, right? In fact, they are called spikes. And the spikes are also called action potentials. They are changes in membrane voltage. So that scale bar over there. And you can see that the signals are very, very small. They are in the millivolt range, meaning 1,000th of a volt. Not enough to light a light bulb, right? And this is how the signals look when you put a probe inside of the neuron. So it's called intracellular recording. And you see these nice signals. And the time course is also very, very fast. So that time course is about 20 milliseconds, which means 1,000th of a second, right? So these are very fast, but very small signals. And you need special equipment to be able to record these signals. So we use amplifiers, which amplify these signals and show them on a computer, where we're able to see these signals like this and record them for later analysis. Same signals can also be recorded extracellularly, meaning you put a probe right outside the cell and you can pick up the electricity using that methodology. And that's how these extracellular signals look. But in this case, because this probe is outside the cell, the signals are much, much smaller in the microvolt range. That means that's even smaller, 10 to the minus 6th of a volt. And the time scales are again in the millisecond range. So these are, I'm showing you because, these are the kinds of data that we generate in the lab, right? And if you look at the nervous system, it's truly a universe within. See, if you take the universe, in the universe you have galaxies, and then within galaxies you have stars and planets, and like our own solar system with a central star and then the planets around it. And within the planets, if you're a special planet like Earth, you could have life forms, and then the life forms have organization. There are populations, there are countries, there are continents. So there is organization at every level. If you go down from the scale of the universe down to the countries and the continents and the people in them, there is organization, right? There is order. It's not all chaotic mix of everything. Similarly, in the nervous system, there is organization at multiple levels. You can start down from the molecular level. Molecules like DNA, proteins, enzymes, all of these things are there, but they're not randomly floating around in a soup. They are organized into signaling networks. So there is, for example, the G protein coupled receptor pathway on neurons, which will collect ligands that bind to them. And then those G protein coupled receptors will then trigger downstream signaling events, make second messengers, and so on and so forth. And those signaling networks themselves will be organized into cellular compartments. So if you take a neuron, the neuron is not a blob. It has a cell body, and then it has dendrites, axons, and the dendrites themselves could have spines. So every little bit of the neuron is well organized, right? And then on top of the neurons, they can be hooked up and made into circuits. Just like if you open a computer, you will see these printed circuit boards with long lines of connections going from one place to another. Look at this diagram of the human nervous system, right? So you have the brain, you have the spinal cord, and then you have the nerves emanating from the spinal cord, reaching various parts of the body, right? And this spinal cord, for instance, is a circuit for producing movement and for sensing where your limbs are. So there are circuits that are present here. There are circuits within the brain, and they talk to each other just like you would find on a printed circuit board in a computer. And all of these circuits and systems work together in order to produce behavior of the organism, be it humans or animals. You know, even the simplest multicellular organisms have behaviors. If you take a hydra, for example, it doesn't have a well-organized nervous system like us, but it has a nervous system to speak of, and it controls the behavior of the hydra, right? So this is how the nervous system functions across scales ranging from 10 to the minus 10 meters all the way to kilometers. Organization on a spatial scale across several different orders of magnitude. Now, questions in neuroscience also involve these multiple scales, and we need a model organism in which we can bridge these scales. And that's why we choose to work on this model organism called zebrafish. And the reason for working on zebrafish are many. Number one, it's a fast growing organism. By 7 days post fertilization, DPF means days post fertilization, the fish is ready to swim and be an independent organism. There is no parental care for fish larvae. In fact, they will eat them if they find them. They will eat their own eggs. So this organism needs to defend itself, find food, and generally grow, right? And by 3 months, it becomes an adult zebrafish capable of laying eggs once again. And also, you know, they are transparent in the early stages of their life. So here is the brain. You can see it directly through the skin. If you put it under the microscope, you can see the individual nerve cells, both within the brain and in the spinal cord. And you can use neat genetic tricks to label neurons, to make mutants, and so on and so forth. And this comes in handy if you're trying to measure activity of these neurons, because there are fluorescent sensors for electrical activity that you can use, which I will probably not today, but you can find on my website. You can find examples of how we measure electrical activity by fluorescence. So that's something that's available. And so we use all of these advantages to ask, how does the brain generate movement? And today I will tell you one short story about what we found out about how animals control their speed of movement. Now, speed is important, right? Because the speed of movement is what helps predators catch prey, like here shown in this video, or the prey to escape from the predator. It's ultimately who is faster and who is more capable of avoiding the predator, or, you know, catching the prey, what is going to happen. So speed is essential for survival, both for the predator and for the prey. Speed is also essential, if you talk about it in a more light-veined mode, for getting your romantic partners. This movie scene may be familiar for many, and you can see that sometimes it's necessary to run faster than a train to find your romantic partner, right? So it's important for you know, the perpetuation of the species. But perhaps human beings are the only ones who will run in vain, who will use speed a gold medal. And this latest fad about catching everything on camera, we are the selfie generation, right? Look at this video. People will run fast to catch things on camera. perhaps even run faster than the runner himself, which is how this cameraman is doing it. So jokes apart, speed, control of speed is essential for survival. But you can't increase speed because there are biological constraints. You have muscles and limbs which you can't move faster than their biological constraint allows them to be. So constantly animals have to weigh energy expenditure with behavioral demand. You can't be running very fast all the time. That is wasteful. That is wasteful expenditure of energy. And so within the constraints of biology, animals have to do this balance between behavior demand and energy expenditure. What do we know about speed control? We know that there are many regions in the brain that determine what the motor command should be. What movement should an animal do at any given point of time? Should they be walking or running? And depending on what these brain centers decide to do, then they set the frequency of motion. How fast should, for example, in humans, the right and the left leg, should they swing? Should they swing very fast like this? Then it will result in running. Or if they swing very slowly, you will get walking, right? And depending on the frequency of motion, just like in an automobile, you can engage gears within the spinal cord. These gears are different circuits within the spinal cord. There are fast circuits and there are slow circuits. And depending on whether you have a walking command or a running command, you get different gears to be engaged. Finally, all of those signals enter this new type of neurons called motor neurons, which are in the spinal cord and send their axons out from the spinal cord to the muscles. And these motor neurons then tell the muscles what to do, right? This is what we knew going into this problem. But what was not appreciated was the role of what is called neuromodulation. These are chemicals like dopamine, acetylcholine, serotonin, and norepinephrine, and others, for example, peptides, many of which I'm not showing, which can be released all over the nervous system, like shown in these colorful arrows, and they can change the state of the brain. You know, we all know how we are in the morning when we are getting up. We are very slow to get up, and then we are walking around. Oh, do I have to get up now? Do I have to really do this? Why can't I go back to bed? But if you're, for example, catching a train or a plane, then you're getting up and you know that you have to get ready in a certain amount of time, and therefore your mental state is different. And therefore, these are the chemicals that are responsible for brain state alterations. So we asked whether such chemicals have a role to play in controlling the speed of movement. So we looked at zebrafish larvae. So zebrafish larvae swim at a wide variety of speed. They can be slow swimmers, like you see this larvae over here. It's just exploring itself, exploring the environment. And they can be trained to swim in one direction by showing them black and white gratings like this. See, the larva is just following the gratings, black and white bars. Or they can swim very, very fast, such as this escape swimming here, which happens over millisecond time scales. Okay, these are different circuitries driving all of these different behaviors. So we took one particular neuromodulator called dopamine, which is known to be present in the spinal cord of these zebrafish larvae. And we know that the dopamine acts via different receptors like D1-like receptor and D2-like receptor. For this talk, I will only talk about the D1-like receptor. And we saw something crazy. What we saw was that normally while zebrafish swim with a certain speed, if you activate the D1-like receptor, they swim very, very fast. So this is like a fish that has been turned into Usain Bolt. It's now zooping along. Compare, it's the same fish between the left and the right, one in normal water and one in D1-like dopamine receptor drug, right? The agonist that we call agonist. See how fast it is moving. So then we asked, how is it that the fish is able to swim faster? By putting them under the microscope and filming their swimming at much higher time and temporal resolution. And we saw that the fish is able to swim faster because the tail is bending over a larger extent. It's swishing over a larger extent. Look at the tail tip here in the top and the tail tip in the bottom, and you'll see that it's bending over a larger distance, giving it more propulsion to go forward, right? So what we then did was look at the command that is generated by the spinal cord. So we can put electrodes on the output from the spinal cord, extracellular recording to you. And what we found was this. So here the grating is stationary, and then when the grating starts moving, it makes a few swim bouts. These are all swim bouts, these black little and when we put the dopamine-like receptor agonist. Look at the size of that command. It's much, much larger, right? There you have it, more than 2 times as big. And we can look at it, look at these commands, these signals at a much higher resolution. And you see that the frequency of these commands is not changed, but only the size of these electrical commands coming out from the spinal cord are larger. Now, this means that the motor neurons could be firing a lot more action potential spikes. So to test that, we put an electrode into the motor neurons in the spinal cord while the fish was looking at these gratings. So we had a screen where we are showing the black and white bars, and then we're putting a pipette electrode into the spinal cord, and we're recording the signals. The little bars here show periods when the grating was moving. And you see that when the drug is put in, the larva makes many, many more action potentials than in control condition. It's all the same cell before and after. And again, the frequency was not different, but only the motor neuron made many, many more action potentials. So how is that possible? So every nerve cell has inputs and then it generates outputs, okay? And it makes some computations here. So it's like a machine. It takes some inputs, just like a computer. You put an input, the computer does some processing, and then it generates outputs. The output is in the form of these action potentials, okay? Now, the same cell in control, when you inject current, okay, it generates only 2 spikes. But when you put these dopamine receptor drugs, it makes many, many more spikes. That means that the cell is now more excitable. So something has fundamentally changed about how this neuron processes information, okay? And that is the key. So there are 2 states, in control and in the cases where neuromodulation by dopamine is present. When neuromodulation by dopamine is present, then the motor neurons are capable of driving high-speed movements. So I won't go into this slide, but I'll go to the summary. We'll skip this. So just to simplify things, what was known already was that there were brain commands which set the frequency of the rhythm, and the frequency of the rhythm resulted in a slow or a fast pace. What we discovered was that you can keep the frequency the same, but using neuromodulation, using things like dopamine, serotonin, etc., you can change the amplitude of the signals, and even by changing the amplitude, you can change speed, okay? So that is the bottom line there. I will end my talk there and perhaps take questions. This is my group at NCBS. We have students from all over the country. In fact, I even had a student from Germany. So we welcome students from everywhere. I should say that typically we don't get many students from Tamil Nadu. It's a matter of disappointment for me. We typically get a lot more students from other places in the country, mostly from metro cities. But Chennai is one of the metro cities that does not contribute a lot of our students in our student pool. But I also have students from rural areas, from Bihar, Uttar Pradesh, Jammu, Kashmir. I have students coming from small town villages. And so, where you come from is not a limitation. It's where you want to go. That is what is going to determine where you end up. Okay. So with that, I will end my presentation. Thank you for the opportunity.
Thank you, Dr. Vatsala. Maybe for want of time, we'll have just few questions. Dr. Mangai.
Madam, thank you for your interesting presentation on fishing expedition in the brine. And you have a question from Kushbu Datta. She asked, even though scientists are able to identify the biochemical or genetic mechanism underlying any pathological conditions of brain, clinical investigation remains a challenge. So what is your suggestion regarding this?
So I assume she is talking about various neurological disorders, neurological and neurodegenerative disorders, and the clinical way to address these problems. See, the problem with doing that is that, as I mentioned in my talk, there are these receptors everywhere in the brain, right? So when you give a drug, it not only affects the circuits and the systems that you want to be probing or you want to be affecting, but it affects everywhere. And it's similar to, for example, maybe it's more understandable if I talk about cancer, right? If you want to kill cancer cells, you need something that specifically goes and kills cancer cells and doesn't kill other cells. The same problem exists in the nervous system in terms of attacking circuits that are malfunctioning, not attacking, but manipulating circuits that are malfunctioning. You need to be able to do that in a way that you don't manipulate or affect activity in other parts of the nervous system. And that remains a challenge. But with more and more approaches to drug designing, designing of molecular probes that will go after only some receptor subtypes and not others, it could be possible. A lot of advances have been made in, for example, different classes of antidepressants, but this is a work in progress, and this is why more research is needed, both to characterize what these different receptor subtypes are doing in different parts of the brain, as well as to design new drug targets to manipulate these receptor subtypes. I hope that answers the question.
Madam, you have another question from Dr. Kavita Tirumurugan from VIT. So what happened to the brain communication of overexcited zebrafish when D1 agonist is overexpressed?
So these are drugs that we applied externally. It's not something that the zebrafish makes by itself. I'm assuming what you're asking about is what happens to neurons in the central nervous system, in the brain. I'm not sure I understood the question properly, but I'm going to answer it in a way that I have understood it. So D1 receptors are present everywhere, but what we did to do away with the effects of other parts of the brain is to have a spinalized preparation where only the spinal cord was present. So we did not affect the other parts of the brain.
Your research work on neurotransmitters, can you help people with Parkinson's disease?
Yes, that's one of the long-term goals of the group. We are looking at ways to utilize the knowledge gained from basic research to see how this can be applied to human health conditions. Definitely, that is one of the motivations for engaging in this kind of research. Not just Parkinson's disease, but also we have other models in zebrafish of, for example, autism susceptibility, candidate genes, and other toxicities that we've followed up.
Thank you, ma'am. Thank you so much for your elaborate talk today, and thank you once again.
Thank you, Dr. Vatsala. It was an interesting talk, and thanks once again for gracing the occasion. Thank you very much.
Thank you.
Thank you. Bye. So we'll move on to the next session. I think Dr. Ritu has joined. Dr. Ritu? Yeah.
Good afternoon to
Good afternoon.
everybody.
Yeah, good afternoon. Thank you, Dr. Ritu, for joining the session. So without much wasting the time, I think we can start the session. And I request Dr. Mangai to introduce next speaker, Dr. Ritu from NPL.
Hello, ma'am. This is Mangai Karasiar from CNR. Today we have Dr. Ritu Srivastava here. Dr. Ritu Srivastava is working as a senior principal scientist at Advanced Materials and Devices Metrology Division at the CSIR NPL. Dr. Ritu has received her PhD from Banaras Hindu University, Varanasi. She has published around 150 research articles in peer-reviewed journals and filed 2 patents. Her research areas includes optoelectronic properties of 2D materials and its applications in fabrications of devices like organic light emitting diodes, organic photovoltaic cells, organic thin film transistors, and organic light emitting transistors. Ma'am has implemented and worked as a principal investigator in more than 10 major research projects funded by CSIR, DST, and DRDO agencies. With this short biography, it's my pleasure to invite Dr. Ritu Srivastava to give a lecture on optoelectronic devices for energy harvesting. Thank you.
Thank you, ma'am, for giving a brief introduction of mine. And first, I would like to thanks to organizer for inviting me for this great events. And I am not wrong, so Swati is here. Maybe she was the student of NPL, and I'm happy to see here. So thanks to Swati also. And she was the bright student of CSR NPL, I would say.
Oh, that's nice to hear.
Yeah. So about my journey to the present designation, it's like I was the youngest child of my family, and the whole world is open for me. I can do anything what I wanted to do, actually. That is I'm lucky in that sense. And I finished my schooling in the small town of Uttar Pradesh, Jaunpur. And after that, I did graduation and post-graduation from there. And then I went to Banaras Hindu University for PhD. And from there, I joined CSR NPL as a scientist. And at that time, our laboratory, that is organic organic electronics laboratory, was under preparation. The job was assigned to me to establish that lab. And from that day, I was working in the area of organic semiconductor devices. Initially, I have started with organic light emitting diodes, then slowly shifted to organic photovoltaic and some luminescence pigment materials. The title of my today's talk is Optoelectronics Devices for Energy Harvesting. My slides are visible there. It is in presentation mode.
Yeah, ma'am, it is visible.
Okay. So as you know that energy is required in every area. It is required for transportation, industrial application, offices, household appliance, agriculture, medical. In every area, the energy is required. So if you estimate the whole world energy consumption, it is approximately 18 terawatt, according to 2017 US Energy Information. And in the India only, the consumption is approximately 1 terawatt per year. So, and for household appliance, if you can see, there are many, the percentage of energy, how much percentage of energy is required. So it is very, so we can say that the energy is mother of all, and to meet all the energy demands, it's a very challenging job. So this shows the how much energy we are getting from different sources, and it is the 2015 data. And so there is a need, because the resources, available resources, are depleting day by day. So there is a need to harvest the energy. Then question comes, what is energy harvesting? Energy harvesting is a process that capture a small amount of energy that would otherwise be lost as heat, light, sound, vibration, or movement. So we can harvest this energy which are going to be waste. So why this energy harvesting is so important? Because our fossil, as I told you, our fossil reserves are depleting much faster, and we need a endless energy supply because of our requirement. And also because of the greenhouse gases and pollution, the conservation of energy is also very important. So the advantages of energy harvesting is we want to need a self-sustainable energy sources, ample energy solution, and which would be readily available, we can use anywhere, and also it should be environmental friendly, and deployment of it's possible. But the area where we cannot reach that, on that place also energy is required. So these are reason why we go for energy harvesting. And the contribution of optic electronic devices is that it generates or conserves energy and also reduces greenhouse gases, reduces pollutions, and it is environmental friendly. What kind of devices comes under optoelectronic devices? It could be photovoltaic, it could be solid state lighting, display, optical data transistor, UV purification system, many more. So if you see the impact of all these devices, the photovoltaic is a renewable energy, reduced carbon emission, reduced pollution. For solid state lighting, its impact is reduced energy consumption, reduced mercury pollution. Similarly, other devices are. Since my main focus is photovoltaic and solid state lighting, in this talk, I will discuss these two devices only. As you know that the global energy requirement is approximately 18 terawatt per year according to 2017 data. And we have a sun which can produce the huge amount of energy. Only thing is that we need a efficient, stable, cost-effective technology to harvest this energy. And the solar cell is a technology that converts solar energy into electricity. And if you see the basic structure of solar cell, it has mainly three components. One is light absorber, other one is carrier collector, and the next one is the metal contacts. The role of light absorber is it converts incident photon to electron and holes. And the role of carrier collector is it captures the carriers and then the transformation of this carriers to the circuit. So you can see the heart of the solar cell is the absorbent material. Depending upon the absorbent material, there are different generation solar cell. First generation, that is wafer based, the silicon solar cell which is available in the market. And second generation is the thin film, amorphous thin film silicon solar cells. Third generation is this low cost and high efficient solar cell, which includes dye-sensitized, quantum dot sensitized solar cell, organic photovoltaic, and the quantum dot hybrid solar cell. And then nowadays we are talking for the perovskite solar cell. So if you see the different solar cell and its characteristics, the first solar cell is an indirect band gap material, most efficient, highly standardized production process, and easily available in the market. But its disadvantages is it is a high cost, create wastage of silicon. When all the panel will degrade, then huge amount of waste will come out. So we have to think how we are going to manage this waste. And the second generation is the thin film solar cell, which includes direct band semiconductor material, lower production cost, flexible material, but it is not much efficient as silicon solar cell. And the toxicity is another issue. Then the third generation cell, it is a tunable. We can tune the band gap also, lightweight, low cost, high absorption coefficient, and work even in a low light conditions. But its efficiency is low, and also degradation in a very short period of time is also a big issue. And the fourth generation, which are nowadays talking about, perovskite solar cell, it is efficient, tunable also, but the issue in its commercialization is its toxicity and stability. So when we are talking about efficient solar cell, what factors are important for that? That is its absorption efficiency, how many photons are absorbed, and then its quantum efficiency. How many photons we are able to convert into electrons. And then energy efficiency, what is the final potential of that electron generated. So if you see the NREL certified efficiency data, you can see how we are increasing the efficiency. And nowadays, perovskite silicon tandem solar cell achieved 29.5% efficiency. So coming out for the organic solar cell mechanism, the excitons forms in the here the ST absorbing material in the active layers, and then it separates. Its dissociation takes place. You can see there are a number of steps: photon absorption, generation of exciton, then exciton diffusion, and hole separation. You can see from this schematic diagram, the exciton formation occurs, then it diffuses towards the acceptor layer, and here it dissociates and then transported. Then there are a different kind of organic solar cell. Initially, we are talking about single layer devices in which only we are using this absorption material. Then to increase the efficiency, people moves towards the bilayer devices where they have used an acceptor material and a donor material. But still the efficiency was not that much. Then since the exciton formation occurs at the interfaces, then they thought we will increase the junction. And then the bulk heterojunction concept was come, and this here they are blending this acceptor and donor material so that the number of junction will increase. But the main challenges which comes for the organic devices is its lower photocurrent, and that may be because of its poor light absorption, generation and transportation. So that is because of photon loss, since most of the photon emitted by the sun is in the range of 1.2 to 1.5 electron. And the absorption of the organic semiconductor material is in the range of 2 electron volts. So most of the photons losses, we are not able to extract all those photons. And then the excitons, the charge separation occurs at the interface. And the excitons have to reach to their respective electrode. So the diffusion length is 10 to 17 nanometer. So if we are able to separate them within that much of time, then we are able to utilize that carrier. Otherwise, the exciton will recombine, and it will give a recombination will take place, and which is not good for solar cell. And also charge carrier losses, and that may be because of the traps, impurity present in the material, recombination, the mobility of the material which we are using, and also the barrier. The interface barrier also plays a very crucial role in such kind of devices. So slowly people moves toward from organic electronic devices to the hybrid photoelectronics devices, in which they have mixed some inorganic material, semiconductor nanocrystal, to increase its high absorption coefficient and to make it more tunable, to increase its carrier mobility and photoconductivity also. So people work on the quantum dots, rod, and then tetrapods. And they have mixed this nanomaterial in the transparent electrodes, hole transport layer, electron transport layer, and absorption. Sometimes they have incorporated the gold and silver nanoparticle also to make a efficient solar cell. So the inorganic nanostructure in incorporated ternary solar cell, people have also worked on it, in which they have mixed the donor acceptor and some nano sheets also, like carbon nanotubes, graphene, like that, to increase its conductivity, to increase its carrier mobility, and other things. So inorganic and organic activities, there people have, as I told you, semiconductor nanostructure material, carbon nanostructure material, metal nanoparticle. They have incorporated and they have make it efficient, try to increase the efficiency. People are not addressing this issue of stability. They are just increasing concentrating on the increase of efficiency. So similarly, they have enhanced the charge transport property by adding the tetrapode shape of nanocrystal, quantum dots, CNT hybrid, CNT and 2D TMD materials, like that, to increase the conductivity and carrier mobility. In the hybrid photovoltaic devices based on the ternary state, we have also made the P3ST PCBM devices, in which we have added the CDSC nanocrystal tetrapods, and we have find out that the enhancement in JSC by attributing that the high electron mobility induced by this tetrapod shapes of cadmium selenide nanocrystal. And then we have investigated the photophysical and electrical characteristic of CI, copper indium sulfur quantum dots and single walled carbon nanotube hybrid structure. And we have found that the improved performance of CIS single walled nanotube nano hybrid device is attributed due to the enhanced charge separation and transportation due to the integrated CIS and single wall carbon nanotube nano hybrid structure, because the CNT will provide a direct path to carrier to reach the respective electrodes. Similarly, we have used this 2D MOS2 nano sheets and incorporated in the polymer ternary solar cell to see the nano sheets contribution. And we have found that the hole and electron mobility was increases with the incorporation of this MOS2 nano sheet, because MOS2 is a conductivity, so it provides the conduction path for conduction. And the mobility of P3ST molecules has been also enhanced by using this MOS2 nano sheets. And the enhancement in electron mobility of PCBM is due to the enhanced electron transport from PCBM to the aluminum cathode via the mobility of 2D network of MOS2 nano sheets. Then we have functionalized this nano sheets of 0 to D hybrid nanostructure to photo-induced charge transfer and enhance photo response. And our observation says that in the presence of light, the current is enhanced by 20 to 50% from CIS quantum dots and respectively respectively. This photocurrent of 0D and 2D hybrid of CIS MOS2 is dramatically increased from 400%. We got a dramatic increase by adding this 0 to D hybrid nanostructure in our P3ST PCBM blends system. And this, when we're talking about this hybrid nanocrystal polymer solar cell, then we are limited by the problem of electron extraction through the nanocrystal network. So the nanorods we have used, and then nanorods have a tendency to lie in the one plane of the field, which is not the optimum arrangement for the electron extraction. So their concept of tetrapods comes, in which in case of tetrapods, at least one leg is upper side. So if there is a path, conduction path is available, we will be able to extract the carriers. So that's why the tetrapods comes in the picture. But still there is a limitation for this hybrid and organic and hybrid solar cell, and that is poor charge transport. Whatever the surface capped insulating ligand is another issue. So people have then the researcher is looking how we can work to overcome all these problems. Then this perovskite solar cell comes in the picture, and which shows a recordable efficiency of 22%. And then the whole research groups are working towards the perovskite solar cell, because they are looking it can be an alternate of the silicon photovoltaic solar cell. And then but there is still a challenge to commercialize this. That is the replacing of this toxic lead, toxicity of this lead present in the perovskite material, which is the people are using less bit perovskite material. So it is another issue to how to overcome with this toxicity of lead, which is the main hurdle to commercialize this kind of material, though the efficiency reaches to the silicon photovoltaic cell. And also the bigger issue is the temperature stability. All the perovskite materials are stable up to below 100 degrees centigrade. So how to overcome this stability as well as the toxicity of the lead, the researcher nowadays working to resolve this issue. And the people are trying very permutation combination to replace this lead, how they are working to replace this lead and find out a suitable material so that they should not compromise with the efficiency. And then the stability. The stability depends upon this perovskite solar cell depends upon its device structure, what kind of device structure we are choosing, and then the photoactive layer, and what kind of charge transport layer we are choosing, electrode material, and how we are encapsulating these devices. There are many factors. When we are exposing it with the UV light, when we are giving it the thermal treatment, moisture, there are many issues we have to address it. So we have also at NPL, we have also fabricated some perovskite nanocrystal and try to fabricate and then we have synthesized some inorganic charge transport layer. So our aim is to make all inorganic cell in which the absorption material should be the perovskite material, and the whole transport and electron transport would be the inorganic material, because organic material has its own limitation. It is a very air sensitive material, environmental sensitive material. So we'd like to change all whole transport layer and electron transport layer with the inorganic material so that we can address this stability issue. And we have fabricated our device by using all this our synthesized nanocrystal, and we have checked our devices for 3 months, more than 3 months, and our device performance remains the same when we are using all inorganic structure. And then to replace this lead, we are working for the lead-free double perovskite material so that with the toxicity issue can be addressed and we will able to replace this lead. Similarly, these all about, I told about the progress of solar organic solar cell and perovskite solar cell, how we have moved towards what is the journey of our in area of solar cell. Now talking about energy convergence, conservation, when we are harvesting this energy, then there is a need that we should conserve it also. So why does lighting impact to energy conservation? A large percentage of total electric energy is used in general lighting. Many at home we are using everywhere. It is a large percentage of energy is used for the lighting. If the energy used for lighting is reduced, it will substantially provide a saving, and also it will reduce the CO2 emission, and which is responsible for climate change. And the progress in the energy efficiency of conventional sources is not changing substantially. And therefore, this area is also very important. So the solid state lighting is the alternative to go for when we are talking about lighting area. And this is the consumption data, how much energy is required for lighting system. And then you can see the LED performance faster than what we are anticipating actually. So what is the advantage of LED lighting? When we talk for LED, it has a long time, small size and weight, temperature stability, fast switching. When we are comparing it with the incandescent bulb and CFL light, it emits cold light and it operates at low voltage. But it has a certain disadvantages also. Like it is fabricated by using a single crystalline material, which has a limitation of area. And also the fabrication process is very costly. So we are looking for alternate of this, and then that's why we are talking for organic light emitting diode, which address the issue of flexibility. We can make in any shape, anywhere, even on the cloth we can deposit this OLED. And also it is a low temperature and low cost, fabrication is low cost. So, and you might have seen the OLED TVs are in the market nowadays. Then what is the advantages? The physics is just like what is the principle. LED is working, the same principle organic light emitting diodes are also working. Its efficiency, when we are talking about the efficiency of OLED, it is more efficient than the condensate bulb, fluorescent bulb, and it is better than all the sources available. And manufacturing process, it is easier to fabricate, faster, brighter, and lower. It can be operated on the lower pro. And the material which you are using to fabricate such kind of devices is also easily available. So these are the advantages of OLEDs. And this is the history of OLED when it was invented. And then this is the structure. It is a 100 to 500 nanometer thick device, and the mainly three components are there: substrate, electrodes, and organic layer. Some other layers like hole similar to the solar cell. Some other layer like hole transport layer and electron transport layer has been used to enhance its efficiency. This is the working mechanism. The charge injection takes place, then its migration. Here we require recombination. In the solar cell, we need separation, and in the OLED, we need a recombination. And then the excitons are recombining and giving the radiative emission, which is coming in the form of light. This is the process how we are fabricating OLED. We are taking a ITO coated glass substrate. It can be a glass substrate. It can be a flexible substrate. What type of device we require, we can choose the substrate of that kind. Then we have to pattern it, whatever the shape and size we are required, whatever the design we required, we can pattern it and then deposit all the emissive layer, STL and ETL, and by applying voltage, we can get the light. This is the OLED roadmap, and by 2012, the flexible devices are coming in the market. And this is how the emission comes. The color depends upon the material of the band gap of the material, and the dopant which we are using. Like suppose if you are adding some dye, it can change the emission wavelength and also intensity and brightness. The device operation is when electrons are injected, and then it moves toward electron and holes are injected from their respective electrode, and then it moves toward in the emissive layer where it recombines, and then radiative emissions are coming. Then how we can optimize the LED efficiency? We have to do the desired balancing of injection and transport of electron and holes. We can avoid current flow without emission, leakage we have to avoid, and the decay at interface we have to avoid. And it is not necessary for here we need a balancing. Means if for each hole we need an electron. Then only we can get a efficient OLED. And also extracting of those photon is very necessary. Suppose if you are able to enhance the internal efficiency of a device to 100%, it is not necessary that we will extract it out. So extraction is also important, and we have to avoid the internal losses inside the OLED. Then only we can get a efficient OLED. This is the characteristic technique which we are using to characterize our OLED devices. And these are the device architecture available for OLED light. It can be bottom or it can be top emission. It can be transparent. It can be inverted OLED, and stacked OLED can also be possible. And therefore, the different kind of OLED market trends, how it is available here. And the today's, in future, the OLED is available in the mobile phone. It is available TV now in the market. And these are the small TVs, large area development, and prototypes are available here. And the future, we can get a paper, the newspaper printed by OLED devices. We can fold it in a pen. So different structure is possible. And this is the new next wave of OLED. We can print on the cloth also. So the place where we cannot provide the lighting, but we can do by this way also. And this is the next decades of lighting. We can make a wallpaper using OLED devices. And there are different companies who are working on this area, and their products are also available in the market. And these are the LEDs which we have fabricated at NPL, different color LEDs. You can see we have fabricated the white OLED also. From here, you can see the natural color of the material which we are illuminating with our OLED. This is the large area green OLED, and this is the 2-inch white OLED. We have made the flexible OLED also, and this shows that when we twist our OLED, it is then also it is working. Different angle we have shown it. And then now I can conclude my talk that optoelectronic devices plays a crucial role in both power generation and energy conservation. Optoelectronic devices is essential in the conversion of sunlight to electrical, thermal, and chemical energy. It also makes an important and significant contribution for reducing energy consumption through more efficient lighting, display, and communication. And this devices touches almost all the area of our lives. So in the both power generation and energy conservation, and it is expected to grow considerably through in the 21st century. Thank you.
Thank you, Dr. Ritu, for a wonderful presentation on optoelectronic devices. May I request Dr. Mangai to ask a few questions, amount of time.
Thank you, ma'am. Thank you for your detailed peresentation on energy harvesting. And Preetham Bharadwaj asked you a question. What is the best solution for counter electrode for perovskite solar cells at room conditions?
Counter electrode, people are using this FTO, one side FTO, and other side where people are using silver. Silver people are using. So I think this now the most of the researchers are working in this by using these electrodes. Gold may be an option, but the cost, we have to see the cost also.
Thank you, ma'am. Thank you so much for your time. And,
okay.
Thank you.
So with that note, on behalf of the Center for Nanotechnology Research, thank Dr. Ritu again for sparing your time and giving a wonderful talk. Thank you, ma'am. Thank you for joining us.
Okay, thank you.
It's a general announcement for the participants. So we'll join exactly at 2:15. I'm sorry for the delay in timing. And one announcement, like March 8 to 13, we have our next event on World Nano Congress on Advanced Science and Technology, WIN-CST 2021. So welcome you all for registering for this event. Thank you. So meet you exactly at 2:15. Thank you.